that experience. And today, I want to mainly talk about some of our recent results on thinking about charge and extern transport, and in particular, how the quantum property of these charge and extons affect this their migration in materials. And I'm preaching to a choir here, so I'm going to be brief on the intro slide, but if you think about energy harvesting in general, whether or not in form of natural system or in the solar cell and other system, is that the how electrons migrate in complex materials is a fundamental important question, right? So like you all think about how, for example, in say things like organic solar cell, how you can migrate extern to the interface so that you can have charge separation, and then you can migrate the charges separately to the electrode. And you would like to be able to potentially like take a movie of like how all these processes occur with simultaneously high spatial and time resolution. For example, you want to know how far your extern can migrate, where are the losses, and how long your charge can migrate, and where are losses, and so on, right? So then when we really think about how electrons, and I use electron here as kind of standing for any energetic particle that you are concerning with, how they migrate in the solid state, you would have to think about, the quantum natures of these particles, right? Because electrons are inherently quantum particle, meaning that they have a wave function associated with them, right? So they have this particle wave duality. So if I start with something that is very simple, right? So like a model system, if I start with, say, a one-dimensional chain of atoms, and is perfect, so there's no disorder, so every atom is exactly the same, and for the moment I'm going to also ignore vibration and fluctuation also, then the wave function of the electron in this 1D chain of atom is going to be described by something is well known, right? Is a one-dimensional quantum box, and that the electron wave function is delocalized over the whole system, and the propagation of the electron is wave-like, right? So now if I would think about, say, a real materials, like for example, if I now replace all these atoms with, say, a nano particle or a quantum dot, if I have a 1D chain of quantum dots, then now the system or the picture looks different now from the perfect one-dimensional chain of atoms, in that one is you're going to have slightly different energy at different sites. So this is known as an energetic disorder. And so now instead of the wave is delocalized over the whole system, what you're going to have is you're going to have slightly different energy of waves, right? So you have wave of different wavelength, and if you add the wave of different wavelength together, you're going to get localization, right? So this is kind of how this is essentially the idea of Anderson localization. So then you're going to have these localized wave packets is now that no longer delocalized over the whole system, but rather only delocalized over a subset of your system, right? So now maybe it's on the orders of a few nanometers, or on the order of a few angstrom, or orders of a few tens of nanometers, all depending on the coupling between sites as well as the disorder, right? And then if you look at the time domain, then you're going to start to have fluctuations such as vibration and or phonons scattering. And so that, what you have now is that in time, the energy of each site is going to change, right? So this is now fluctuation in time. So if you really want to understand how the quantum property, or whether or not you can access the quantum regime, how these energetic particle move around in materials, then you would want to be able to ideally have a spatial resolution that is as small as their wave function, the extent of their wave function, so you can probe within the wave function, right? And then you would also want to have time resolution that is faster than any fluctuation in the system, like vibration or phonons. So ideally, you want something like a femtosecond time resolution and nanometer scale spatial resolution. And getting to the spatial resolution on the order wave function is hard. So we are not there yet, but I'm going to tell you today, like kind of where we are at and how we can actually address like how we can utilize or control transport energetic particles using quantum mechanical properties of these particles. And so to start off, I kind of mentioned that, femtosecond time resolution is relatively, I guess, easy because we have this femtosecond lasers, and many of you are familiar with. And so if you use these lasers as a shutter, then you can, for example, image how light propagates in a Coca-Cola bottle. And this is a movie taken by the MIT Media Lab. And so by naked eye, you cannot see this because this whole thing, right, because will end in like 10 picosecond or so, because light propagates with speeds of light, of course. But if you take this propagation with femtosecond lasers frame by frame and slow by 10 billion times, then you see this beautiful video as I show. So in our experiment, what we are interested in is not just light propagate by itself, although that it is a very interesting topic, but we are not interested in that. But what we're interested in is in the this excited charge carrier or exton, like generated by light, and how they propagate. So then what we need is actually we need two laser pulses, and this is by the mean of Pompo method, which many of you are also familiar with. So you can use the pump to excite your molecule or material into the excited state, and your probe pulse then serve as this shutter that to capture the motion of these carriers or extons. And in order to form an image of how this carrier migrates, then what we do is we can either focus both pump and probe beams into an inverted microscope, and then use a galvanometer scan mirrors to spatially separate the pump and probe. So you can imagine an experiment where you pump and locate one location and probe at the other, and to watch how the charge carrier and exton migrate. We can also do in a wide field geometry where the probing is wide field and the pumping is focused. Both works, and they have different advantage and disadvantage. If you're interested in the technique, we published a review article a few years ago, and you can check it out. And one thing I just want to say is that the all this is done in far field, the focusing and detection both in far field, so that the pumping size and probing size are going to be limited by diffraction. But I'm going to show an example later that, like how this charge carrier and exton migrate, we can actually probe with much better spatial resolution on the orders of tens of nanometers. So in the past, probably like 8 years or so, we've been looking at different classes of materials, including hybrid perovskite, quantum material, and molecular exton. Today, I'm going to talk mostly on some of the hybrid perovskite work and 2D material works. And see how far I get to. Okay, so the example I'm going to share today, I'm going to start with perovskite. These are 3D perovskite. So in that the lattice are continuous. So if you might think that the in the picture that I showed before, the coupling between side, the J, the coupling between side is the ionic bonding between atoms. So these are pretty strong coupling. So you would imagine this type of materials would have more like a band-like transport, right? But in the system, of course, the disorder come from like structural disorder and things like phonon scattering. And then I will use that mostly as an example of kind of setting up the methods. And the next example I'm going to share with is like if we chop this perovskite into tiny quantum particles and then make lattices of them. And then now your J coupling, instead of this bonding between sides, now you actually is gonna looking at a smaller coupling, which is extonic coupling between these quantum dots. And then it gives us an example of how we can control the coupling versus disorder to control the extonic wave function. And last example, I don't know if I have a time, but it's another way of creating exton superlattices, and really to look at if I change the coupling is so small, and then I induce a barrier between them is so high that I'm going to localize these extons. So instead of delocalize them, I'm going to localize them and looking at many body interaction. So keep trying to give these different facets of like how we control the interaction between these quantum particles and affect their transport properties. So since I'm the first talk, I'm sure you're gonna heard about more about hybrid perovskite, but you probably already heard about them. But I'm just gonna here give the key thing that are important for our experiment. One is that they are exceptionally great solar cell materials, but actually it's kind of surprising how good they are, because these are solutionally processed semiconductor at low temperature. So you would expect a lot of defect and disorder. So like large omega in the picture I show. And so hence you would think that they don't, the charge don't migrate very long. But of course, charge migration in materials is very efficient. That's why you have very efficient solar cell. So the question is why, right? So why this charge migration in material seem to be robust against defect and disorder? So to do that, we want to kind of look at, okay, how long can this charge live and how fast they can migrate and what happened to things like, disorder and whatever. So to do the experiment, this is kind of what I have described earlier by words, is that we will focus the pump being in the center and scanning the probe relative to it to form an image. The color is arbitrary, so we have tunability and pump and probe in so that we can probe different resonances. So in this case, we're gonna probe near the band gap, so which is about 1.67, so right at the band gap, looking at this band edge carrier. And the initial experiment we did is just to look at this sort of long time behavior. So on the orders of nanoseconds, and you can see that early time. When we excite, these are also excite very close to the band gap. So early time, the image really shows you essentially the pumping, right? So the area that you generate this charge carrier. And in the bulk perovskite or 3D perovskite, and this is methyl ammonium lead iodide, the external binding energy is rather small, it's about 5 to 10 millieV. So at room temperature, roughly, you can assume they are free charge carriers. So as time progresses, you can see this gets bigger and bigger, right? And that has to do with this charge carrier migrate from where it was initially excited. And if we take a slice of this image, then we can build this Gaussian curve as a function of time, and then expand as function of time. And you can describe this by a pretty well-known equation that describes diffusion of any particles. So you will have a diffusion term, the spatial and time dependent of its carrier distribution would have controlled by a diffusion term and a recombination term. And the solution to this is also pretty well known, so that if you would plot the variance of Gaussian as a function of time, it should be linear, and the diffusion constant is directly given by the slope of this linear relationship. So in perovskite, 3D perovskite, this is single crystal, we see a diffusion constant on the orders of 1 centimeter square per second. So this gives us a way of directly measuring, charge carrier migration in time. But the kind of the more interesting thing that perhaps, as I was sort of alluding to in earlier, is that can we also probe in a regime that where is not described by this classical motion of particle, but rather have the wave part of this particle still matters. So this would be, for example, like if you're probing the high energy carriers, if we excite very, very high up in the band gap, because this high energy carrier, before they get scattered by phonons and so on, their wave function is very delocalized, and they will have very high momentum, so they can propagate in a wave-like manner with very high speed. So we set out to do this by the example I showed you before is excite right at the band gap, but now I want to excite much higher in the band gap, right? So if I go from 1.7 electron volts to 2.7 electron volts, what I start to see is that I would see this hard carrier have a new absorption band just right below the band gap. And this has to do with the hard carrier induced some band gap renormalization. And so this is kind of the regime that when you think about in this carrier's lifetime is that very early in their lifetime is that when there are only maybe a few or just one scattering event, right? So they still maintain their wave-like properties and has a well-defined velocity. And so this is in the ballistic regime, you may call. And so then if we look at this high energy carrier at very, very early time, then so this now is focused on the first 1 picosecond. And what we see is that if it's excited very high up, we will see this carrier migrate very, very fast. So this color scale, blue is the absorption and then red is the bleach. So recall from the last slide, the hot carrier has a induced absorption band right below the band gap. So this is kind of why you see it's all blue in early time. So if you would lower the pump energy, so now you don't give the carrier so much excess energy, then they don't migrate as fast, right? So we can then also deduce from this measurement that this hot carrier can migrate in the first 300 femtoseconds about 250 nanometers, which is remarkable. That means that they have a velocity on the orders of 10 to the 6 meter per second, which is pretty fast. And that would also mean that this high energy carrier can be potentially harvested in a hot carrier solar cell, because for perovskite solar cell, they only need to be about a few hundred nanometer thick. So again, to summarize like what we have learned in the perovskite example is that if we look very early in time, we can access this ballistic regime, whereas very few scattering events. So the quantum property of this particle is very important. And if we look at a later time, right, if we get to this coherent, incoherent or more the classical diffusive regime, that it's and if you look at the distance that propagates, the diffusive regime has this well-known relationship as proportional square root of t. In the ballistic regime, the distance that it travels is proportional to t, right? So if you do a time resolved measurement, then you should be able to differentiate these two regimes. And indeed, if we, even if we excite very high up and we look at longer time, like on a nanosecond time scale, we do see initially this is the ballistic regime or quasi-ballistic regime, and on later time, it does become this diffusive regime, right? Because after you have enough scattering event, it does come to this more classical limit of diffusive transport. I hope that I have shown you in this example that we can use this time resolved microscopy to really differentiate different transport regime. And next, I'm going to go to the example that if I would trap this perovskite into tiny chunks and then make them into nanoparticles, this perovskite quantum dots are actually gather quite a bit of interest because they are just excellent light emitters. They have very large oscillator strength with a exciton state, the lowest exciton state being a bright state, so they have emission quantum yield that's very close to 1. So then we are interested in them because if they do have large oscillator strength, that means that you can introduce a large coupling between them. So that these are the questions that I raised in the beginning, that can be sort of control the coupling between this quantum dot as well as the disorder in the system to induce a delocalized exciton state that is over multiple quantum dots. And in this project, we collaborate with Professor Christina Lee, who is a colleague of mine at Purdue. And Christina can grow these super lattices of these quantum dots in that you can see that this large crystal, this is on micron size. They are made up of many of these tiny quantum dots. And you can see in this little speck are these quantum dots. And they form into superlattice, meaning that they have well-defined interparticle distance, as you can see from the diffraction pattern. So the quantum dots themselves are about 9 nanometers in diameter, and the organic ligand between them is about 3 nanometers. So the inter-quantum dot distance is about 12 nanometers. And they have enormous transition dipole on the orders of 90 dBi. And so like they can induce like this coupling, dipolar coupling between these excitons about 20 millieV. So if this 20 millieV is larger, then say the energy difference between sites and as well as the fluctuation in time, then what you can have is that you can induce a collective or delocalized exciton states just similar in the way of how you form a hydrogen molecule from two hydrogen atoms, right? So you form this binding and anti-binding state with the binding state had slightly lower in energy, and the energy difference between the isolated quantum dots and the collective state is roughly on the orders of the coupling. And so first we want to do some low temperature because we want to see how it competes with phonon scattering, right, as well as these energetic disorders. So we need to do low temperature dependent measurement. And indeed, this we use the wonderful CNM user facility with Dr. Rich Charlotte here, and what we did with Rich was some of these measurements are done in our lab and some is done at CNM. And what we did is that let me look at two samples. One is the superlattice, one is these isolated quantum dots just dispersed in a PMMA matrix. So what we see is that if we go down to low temperature in the superlattice, this emission becomes redshifted and much narrower, and compared to the isolated quantum dot. So at room temperature, the line width and the peak position of the superlattice and the isolated quantum dot are roughly similar, but at low temperature, they become much narrower and redshifted. Redshifted is coming from what I was describing before. And by the way, we also ruled out things like energy transfer in the system and so on. And the narrow line width is also telling, because that has coming from what's known as exchange narrowing, similar to what happened when you see delocalized exon state in molecular aggregates. So if you have exon delocalized over multiple sites, the inhomogeneous broadening can be reduced because you can average the contribution from multiple sites. So the fact that we see a both narrow and redshifted emission in the superlattice, indicating that we form some states that are more delocalized at low temperature, right? And these states are formed at low temperature because you need to overcome the phonon scattering as well. So, and the kind of a more indicative way of really definitely showing that these exons are delocalized is also to look at the radiant rate of in this collective state. So if you form a collective state, which I shown schematically down here, in that the state can be think of it as a superposition between the exon is site 1 plus site 2 and plus site 3. The radial rate will enhance by the number of the couple exon because you enlarge the transition dipole. So because these exons, these quantum dots are actually very close to quantum yield 1, we can extract from the PL time result PL measurement their radial rate. So what we see is at room temperature, the radial rate in the superlattice and the isolated quantum dot are roughly the same. So meaning that the exon at high temperature is localized to one quantum dot, but at low temperature is become 3 times larger than the isolated quantum dot because of the exon becomes delocalized over multiple quantum dots. So this actually gives a definitive measure of how delocalized these exons are, and they're on average over 3 quantum dots. So now we have a system that now we can really look at how this delocalized exon wave function propagates in a complex material like a quantum superlattices. So to look at this, we collaborate with an expert in quantum transport, Professor James Ruchow, and he's a former student Chang at MIT. And so when you think about like how exon would migrate or in a delocalized wave function, is that within the segment, right? Like within this delocalized segment, you would imagine the exon will propagate in a wave-like manner, right? And between the segment, they would have to hop. And this hopping would have to require thermal energy or some fluctuation. So like so then you're going to have some competition, because at very low temperature, your exon is most delocalized. But at very low temperature, you're going to have very little thermal fluctuation to help you to hop between the segment. So what you expect is that at a short time limit, at low temperature, everything is going to go faster because the exon is more delocalized. But at a long time limit, it's going to be a balance between how delocalized your exon is versus how fast you can hop between the segments. So like you should expect a maximum in the long time transport at a certain temperature is a balance between how delocalized your wave function is and how far you can hop. And from Jianshu theory, this temperature, the maximum hopping rate at the long time limit is going to be exactly when the thermal dephasing is equal to energetic disorder. So then I'm going to skip this. So then we set out to look at this directly. So then these are the quantum dot superlattice I showed you before. And at 6 Kelvin, we can measure it down to as low as 6 Kelvin. And then if we look at, this is time dependent, this is the sigma square or how far the exon can migrate. So it's exactly like what Jianshu had predicted. If you look at the early time, if you look at the very early time, things are much faster at low temperature, right? The 7K and 11K are much, much faster than the 295. And everything decreases as a function of temperature at early time, right? That's because your delocalization is going to decrease as a function of temperature. But if we look at the long time behavior, like say at 4 or 5 nanoseconds, you're going to see that at very low temperature and long time, nothing is really moving because you cannot really hop between those delocalized segments. But you're going to see a maximum at certain temperature, like in this case is 158 Kelvin. And because that's when the thermal dephasing is exactly balanced out by static disorder, as Jianshu had predicted. So if we plot this diffusion constant as a function of time and temperature at different temperature, and we'll see that at low temperature, you're going to have a very fast diffusion at early time, and it peaks out and then it decay. And at higher temperature, it becomes more or less just like diffusing. And this is exactly like similar to what Jianshu had predicted in his theory. So at low temperature, you have this kind of initially rise and then decay, and at high temperature, you kind of just have a flat curve. And then we sort of exactly, this is on the right is a theoretical prediction, on the left is experiment, that we also see this maximum diffusion constant for a long time at a certain temperature. And if you would compare, I know I'm almost out of time, so this will be my last slide. If you will compare a system where it's totally disordered, so you don't have any exon delocalization. So this is just a disordered thin film. So your exon is just localized to a single quantum dot, even at very low temperature. Then what you see is your diffusion constant as a function of temperature is going to monotonously increase the function time, right? Because to move between this quantum dot, you're going to have thermal energy to help you to hop between them. So I don't have time to share with you the last example, but I just want to kind of summarize in that, with time and spatial resolution, then we can really access some of this quantum regime of transport and really understand how we control the interaction between these quantum particles to manipulate their transport behaviors. And last but not least, I would like to thank the student who did the work. The 3D Pascal work is mostly done by a postdoc, Shibing Deng, and the quantum dot superlattice is done mostly by 2 grad students, Daria Blanc, who just recently graduated, and as well as Victoria Lamsadres, and both of them actually have visited Argonne and worked with Rich and Gary. So thank you very much for your attention. I'll be happy to take any questions.
Thank you very much, Tobias. That was excellent. Maybe we have time for one question. Oh, someone can ask it.
We talked about it. I just thought I'd ask a real quick question, which is when your charges in the part with in wonderful talk, in the part where you have the charges moving at very high speed, I guess what I'm wondering about is things like intraband relaxation, or with your viewpoint on how fast intraband relaxation is, and if there's like thermal energy deposited, and if that plays a role in addition to or things like the high speed of the actual carriers. So I just wondered if you could comment on that a bit more.
Yeah, for sure. I mean, so that, as you go higher and higher in energy band, you also have higher density of state, and usually your phonon scattering and intraband relaxation, as you mentioned, will get faster. And in general, in things like silicon, yes, those time scales are on the order of 10 femtoseconds. So you would lose this ballistic transport pretty quickly. But I think what's kind of somewhat special about Pascal, and this is, I know that you also work a lot on this kind of question is somewhat special. I think like electron photon scattering in perovskite is different than say some of these more conventional materials, and that from calculation, what people have shown is that this high energy carrier, even if like 1 electron volts above the band gap, the scattering events are on the orders 100 femtoseconds. So like on the time scale of Van Pro, like they might have one or few scattering event, and they'll still be mostly ballistic, or at least quasi-ballistic, I guess. They're not quite diffusive. Yeah.
Okay, great. Thank you very much.
Okay, I think in the interest of staying on time, we have to move on, but that was a great talk, Levi. Thank you.
Thank you, everyone.
Bye. So Renaud Bachelot, the co-organizer of this workshop, has overcome his connection issues and plans to chair this morning session. So he's a professor at the University of Technology at Troyes with a lot of expertise in the nanophotonics area. And again, he will take over the chairing of the rest of this morning session.
Thanks, Gary, and sorry for being late. I could fix my problem. So I am happy to present the next talk that is going to be given by Claire Xiong. So the talk deals with metal oxide electrode materials.
Hey, thanks for the introduction, Renaud, and I also appreciate the invitation from Gary and Renaud. So I did my postdoc at CNM, so it's feel like coming home. Although I feel it will be better if we have the in-person meeting, so we can visit the facilities, because we have kind of stopped going to the facilities. Just send a student over, but I hope we can have more chances to going back and forth a bit between Argonne. And the talk, my talk today is about nanoscale amorphous metal oxide electrode and their implication and applications for lithium-ion batteries. First, I would like to thank my students and postdocs. Without them, and also my collaborators. Without them, we couldn't do the things we are really interested with. And I also would like to thank my funding support from NSF and RRC, as also the support from the user facility like CNM and Saint. So just a little bit of what we do in our group, the Electrochemical Energy Materials Laboratory. So we are trying to use different ways to make nanomaterials using either the electrochemical method, colloidal method, and also hydrothermal and solventothermal method to grow different nanostructures and heterostructures. And one of our kind of focus is trying to understand the role of defect. So it's really interesting to see Levi's talk about how to using this unique technique to follow the kind of evolutions of the defect. So in our case, we're trying to see how we can manipulate the defect and understand their electrochemical properties for applications such as lithium batteries. And we're also interested to understand the interface and the heterostructures, how we can utilize the composite nanostructures and then to enhance their electrochemical properties. As Levi mentioned, it's very important that you need to follow the process or phenomena from the beginning to the end, right? So we also try to see if we can use the in situ and operando characterizations to try to capture those very complex processes, especially in the battery systems. So for my talk today, I'm trying to kind of discuss our studies of the defect-driven electron materials, and if the time allows, we also want to kind of discuss what we use ion irradiation to kind of create a defect and how to understand the defect's role for their applications for lithium-ion batteries. So probably everyone already knows, like it's very important for the energy storage system that it's ubiquitous in our daily life, and we also have a lot of demand for the energy storage system. Like we want them to provide us as high of the energy we could, and also as fast as we can. So there's a lot of like increasing demand for the energy storage system in order to provide high energy and power densities, and also you want it to last long and with low cost, and also safe, and with environmental sustainability, as now we have a lot of discussion about the critical minerals and also the supply chain risks. So there's a lot of effort in the field is trying to develop materials that use most earth abundant and more sustainable materials. Just for those of you who are not working in our field, so there's a kind of the general principles for lithium-ion batteries. We have the lithium-ion. It's a reversible. It's a rechargeable battery. Means that during discharge, the lithium-ion will move from the anode or the negative electrode through a ion conducting, usually electron impeding, usually a non-aqueous electrolyte to the cathode side, or also the positive electrode. At the same time, the electron will transfer externally to satisfy the charge neutralization, and then the same time provide the electricity, and vice versa. And because I'm an electrochemist by training, so we always think about anything, if it's an electrochemical cell, it's a collection of interfaces. So there's no exception for the battery system. So the battery system, we also have this anode or negative electrode in contact with the electrolyte, and also in contact with the positive electrode. So there's a kind of alignment of their energies. So we need to, ideally, we would like the energy of the negative electrode to be lower than the lowest unoccupied molecular orbital of the electrolyte. And for the positive electrode, we want it to be higher than the highest occupied molecular orbital. But in reality, we actually usually, most of the time, we operate outside of the thermodynamic stability window. So then we have the extra layer to form. So like at the anode side is a solid electrolyte interface, and the cathode side is a cathode electrolyte interface in order to kinetically to make the interface stable. And in terms of the electromaterials design, because we want to maximize the energy densities, we want to have the electrode to have high capacities, and also for the negative electrode, we want it to have a low potential, and positive electrode, we want it to have high potential in order to also maximize the output potential. And in terms of the different structures for the electromaterials, there's a three main type. One is insertion or intercalation type. So for this type of material, they have a vacant side. So the lithium or other transport ions like sodium, they can go to the vacant side and then provide the charge storage. And there's also anion type such as silicon and tin. They can form anion with the lithium, and usually they have a very high theoretical capacity, but because of they undergoes a huge volume change, so there's issues with cycling stability. So conversion type of material, they undergo conversion reactions, and similar to anion type of electrode, they also have high theoretical capacity, but also undergoes a huge volume change during charging, discharging. So one of our kind of interests is looking at the different negative electrode or the anode for the lithium-ion batteries. So we have talked about there's a different metrics for good negative electrode. We want it for sure to have a high energy density, power density, and we want it to have a low volume change, so they don't undergo a lot of stress during cycling, and that can promote for their better cycling stability. And we want it to be low cost, and also have a good cyclability, and be environmental friendly. So for our interest here, we'll focus on the intercalation or the insertion type of materials. And compared to the commercial graphite anode, the metal oxide, which is usually the intercalation type of electrode, they provide a comparable like a theoretical capacity compared to graphite. One of the benefits for this metal oxide is they usually operate at a little bit higher voltage compared to the graphite electrode, so they have less of the issues with lithium plating and later on the lithium dendrite formation and thermal runaways. So they could be a safe negative electrode for the lithium-ion batteries. But they also have their own problems. Usually for the metal oxide, their conductivity is not really good, and their power performance is not as good as well. So for our for my group's pursuit of the defect-driven electromaterials, actually step back from my postdoc studies at CNM almost more than 10 years ago. At that time, we discovered that when we put the amorphous titanium dioxide electrode into cycling with lithium, it starts to form this unique cubic structure that shows a better performance than the other titanium dioxide polymorphs. And at that time, about the same time, the group at the Naval Research, they also published perspective and called the attention of the people in the field to look at the cation disorder of the different electromaterials. And also Cedars group, they published this very phenomenal papers for the disordered cation disordered oxide for looking at the defect-driven electrode materials for the rechargeable batteries. So if we look at the lithium, if we look at the titanium dioxide polymorphs, so anode and rutile are the most popular structures that's used for lithium batteries, and they are for the anodes, it contains those 1D zigzag channels for the lithium diffusion, and usually for the bulk of the anodes TiO2, they can uptake like a 0.5 per unit formula for the TiO2 for lithium. And for the rutiles, it's through the channels diffusion for the lithium. And the other thing is very interesting from Dr. Alex Nabraski's group. They did thermodynamic studies to look at the phase stabilities based on the size of the TiO2 particles. So from their study, you can show that if at a bulk size, the rutile is the most thermodynamic stable phase. And if you go to like a larger surface area, meaning that your size go to like a nano size, the anodes becomes the most thermodynamic stable phase. So this also leads us to think about the thermodynamic stability of the materials if you change the size of your of the same chemical composition, right? So there's a thermodynamic stability can change based on the size of your materials. So in our case, like when I think when over 10 years ago at Argonne, we noticed this kind of interesting phenomena. This is a typical voltage profile for the amorphous TiO2 electrode. When we subject this amorphous TiO2 electrode into cycling with the lithium in a half-cell setup, we start to see, like using the synchrotron XRD, we start to see this amorphous structure phase change to a cubic structure. And this is also indicative by this hump of this voltage profile. And what is very interesting is that even after the lithium comes out, this cubic structure still maintains. And we also did synchrotron XRD and X-ray absorption spectroscopy to see this structure is what we say is a long-range ordered, short-range disordered, and it also shows a higher higher capacity compared to all the other TiO2 polymorphs. So this is lead us to a kind of very interested in this amorphous to crystalline transformation phenomenon. So we also later on did a refinement and find out that this cubic structure is actually a rock salt structure, and it also shows very good rate capability. So our question is, then this structure seems like probably is a metastable phase. So where it will sit in this plot, when we have this size of the TiO2 go to the nano region. And we also kind of based on this result, we have this kind of hypothesis. We think like if we have this amorphous structure as a framework, and then we have this stimuli, for example, like lithium ion to interact with the titanium and oxygen. And if we have enough of the concentration of this titanium lithium to bombard on this titanium oxygen framework, they will eventually to a kind of a phase transform to this ordered structure, like long range ordered, short range disordered. So at that time, I just think about this hypothesis. Can we use a nanostructured amorphous as a free? Can we use an amorphous nanostructure as a framework so we can alter their structure and then they can just self kind of organize into the optimal structure? And for the application, for our case, is lithium storage to show the better performance compared to the other already formed rigid structure. So my friend Henda and also I think colleague at CNM, Subramania, and also Jeff Grilling at that time, they did a DFT calculation. So they also look at the TiO2 nanoparticles. In their case, they're looking at a 6 nanometer TiO2 nanoparticles. From their study, they also see there's a strong intra-particle lithium segregation in the TiO2 amorphous nanoparticles through their MD simulation. And this degree of segregation is correlated with the lithium concentration, meaning that if you have probably the segregation is large enough, you have high enough lithium concentration that might initiate this localized atomic rearrangement that eventually can cause this phase transformation to this, for example, the cubic structure. So my interest is we have seen this phenomena in the nanotube system. Can we see that in other like nanostructured system? So in collaboration with Professor Yadong Yin at UC Riverside, we use the method that they developed using a water-assisted wet chemistry to synthesize the mesoporous TiO2 nanoparticles with controlled crystallinity. So we also use a synchrotron pair distribution function to look at their local structure change. And what we see is if we have fully crystalline TiO2 nanoparticles, it just shows the typical behavior like anatase TiO2 electrode. You have this two-phase range around 1.7 volt. But if we change the crystallinity to become like a partially crystalline, then you see this disappearance of this two-phase stage. And once it becomes amorphous, you just see this solid solution kind of mechanism, which is typical of amorphous materials. And we also did a PDF to see the local structure change. So what we found is actually it's the change of the second shell. So meaning that we are looking at the titanium along this transport channel. So what we see is in this case, this crystalline electrode still shows a better transport kinetics because of they have this enlarged the titanium distance. And we for this system, we also don't see this amorphous to crystalline transformation. So it's still kind of intriguing us, like what is the kind of critical conditions we can see this phenomenon of this amorphous to crystalline transformation. And we did further studies, and right now we also see the indication of this change, but we're still trying to kind of figure out what is the exact condition. But it looks like this is this metastable phase is related to the rate how we put the lithium in and out into the system. So there's a lot of different factors that could affect this transformation phenomenon. So our next question is like we see this in this titanium dioxide system. Is that only applied to this TiO2 system? Can we also see that in other like potential metal oxide electrode? So our next kind of quest is to look at niobium, because niobium is also known as a good electron materials for energy storage system. And so my former graduate student, Pete Barnes, also worked on to use the electroanodization to form this ordered amorphous niobium oxide structures that we use we use it as a framework, like I proposed earlier. So what we look at is this is a voltage profile, and this is a differential charge over voltage profile. So you can think about it similar to the cyclic photometry. What is interesting is we start to see this hump to form, which again indicative of this phase transformation. And the interesting part is we see this hysteresis between charge and discharge kind of decrease with the cycles, and also you see this. You can see this peak-to-peak separation start to decrease with cycles, which suggests these materials phase transform, and with cycles it actually improves its kinetics. So this is a very very interesting. We are very excited to see this phenomenon in the niobium system. And also we did further studies to see to show that at the first cycles they start to form this nanocrystalline, and with additional cycles they actually becomes a fully crystalline. And we also did XRD to show it's a rock salt structure. And it also from the XF, it shows this improvement of the local ordering. And we also are curious to see how this structure will change at a different state of charge. So we also did the TEM, that's use the facility at the CNM, and to show that this structure maintains the rock salt structure at a different state of charge, meaning at a different lithium concentration, and also at a different cycling. So meaning this structure maintains. And we also did further investigations to look at their charge compensation by using ZENS and also XPS. And what we learned is actually this niobium oxide actually has a multi-electron transfer. So usually for what has been reported for the niobium oxide system, usually cannot go beyond 1 electron transfer per niobium. So in our case, we have around 1.3 electron transfer per niobium. So that also is reflected by its high capacity compared to the other niobium polymorphs. So in collaboration with Professor Shiping Wang and his student at the UCSD, we also did the DFT calculation to look at their to understand the mechanism for the kinetics. So what they found is for this newly formed rock salt structure, they actually undergoes this octahedral to octahedral hop, which is different from this octahedral to tetragonal octahedral hop, which is usually found for the DRX, the cation disordered rock salt structure for the cathode materials. And they also showed that if you need to have a high concentration of near niobium in order to promote this kind of high lithium diffusivity. Okay, so then so far what we have found that the amorphous to crystalline transformation, we observed that in the titanium system, niobium system, and Dr. Shiping Wang and Professor Ping Liu at UCSD also reported this phenomenon in the vanadium oxide system. And there's also work by Professor Hailong Chen in Georgia Tech. They also showed for the manganese oxide by electrochemical cycling, they can form a rare structure which is not usually accessible through a conventional synthesis method. So then we kind of coming together, we can start to think, actually, maybe it's a good way that we use amorphous or nanostructured amorphous materials as a platform or framework, and that we can flexibly transform into a optical crystal structure that can show better electrochemical properties. So Shiping has done a DFT calculation to try to predict what will be the next materials that we should try. And from his calculation is we look at, he said titanium oxide would be the next that we probably will see this transform. And actually, just recently, we also proved that titanium oxide also have this amorphous to crystalline transformation. So we are really excited to see that it is through this electrochemical cycling, we can form a kind of a rare structure which is usually not attainable through conventional synthesis method, and which is metal stable but shows a very good electrochemical properties. Okay, so I think I still have a few minutes. I have showed through electrochemical cycling. So we kind of use it this year as a stimuli to interact with amorphous metal oxide framework for them to kind of cell arrange or undergoes atomic rearrangement to form this optimized structure. So we are also interested in, do we have other ways that we can change the materials structure? So another thing is we have done quite a lot is also looking at the ion irradiation effect to see how the charged particle or the energetic particle, the interaction. So this time we are looking at the ion irradiation as a stimuli to the metal oxide framework to see what their response is. So, so this is usually what we are thinking is to based on the different interaction. So the charge, the energetic particles, they can have the energy loss with your target material, either through the electronic energy loss or through nuclear energy loss. And it could have a combination effect of both the nuclear and the electronic energy loss. So actually from our study, we actually see this phenomena that we have a amorphous, again, TiO2 nanotube, because we like it as a model system. And we did a proton irradiation. What we found is after proton irradiation at 250 degrees C, we see this transform of the amorphous TiO2 nanotube to disordered rutile phase, which also shows a better electrochemical properties. And we also, for comparison, we also did just anatase TiO2 to compare with amorphous TiO2 nanotube. So for the anatase TiO2, after proton irradiation, it didn't go back to amorphous. It actually created more defect and also has improved electrochemical properties. So this is again we are very interested in related to this mechanism or the energy loss mechanism. So if we think about this energy injection of the energetic particle, like your ion irradiation, to your amorphous matrix, right? So we also have this energy export. So if we think about the incident energy, so the incident energy is delta En, right? Can be stored as a defect, so still in the disordered state, and it also can be stimulated. So it can also be stimulated, but this stimulated state want to go back to a lower energy state. But usually it's not going to the original amorphous state, but it will go to a lower energy through rearrangement to a crystalline phase. So now the kind of the energy difference would be this equation that we have the delta Et over the minus delta Er plus delta En, and this delta En is the incident energy, and this delta Er is the energy under the atomic rearrangement. So if we have a sufficient number of those stimulated atoms here, they can then arrange themselves during the irradiation. So we can possibly have this delta Er bigger than this delta En, which means that can promote this this atomic rearrangement to form a new crystalline structure. So this tells us probably we need to manipulate this energy input and output to see how we can change the structure. because I have a limited time, I will just do it fast. And so like I said, we have this interaction of the electronic versus the nuclear. So they also happen at a different energy level, and also it is related with the particles. For the lighter particles, usually you have a stronger electronic interaction, and for the heavier particles, you have a stronger nuclear interactions. So this is just to show, like for the I think this is for TiO2. If we do a krypton irradiation at 46 keV, we probably have more of the nuclear stopping nuclear interactions. So in collaboration with my colleague January at Purdue, we are doing a series of ion irradiation to trying to figure out the effect, how that change the structures of this amorphous nanotube. And I'll skip that and then go probably skip this too, to show that through using different ions, we see like for this 46 keV gold ions, we see this nanocrystalline transformation. And when we do the same energy with a krypton, we see this structure stays amorphous. And when we use a heavier, also inert ions, we start to see these nanocrystalline formations. We also did an electron irradiation and also start to see this amorphous to crystalline transformation. So to summarize, we just say that the irradiation different from what we do the thermal anneal. So it's a thermal phenomena. We can form a metastable nanocrystalline structures through manipulation the ion irradiation that can be useful for use of nanomaterials for other applications. With that, I'd like to thank everyone, and I'll be happy to answer any questions.
Thank you, Claire, for this great talk. So we have time for one question, because it is 10:10. Question, yeah, Konstantinos.
Thank you for the nice talk. Can you control the amorphization? Can you amorphize partially the structures?
So you mean, can I do the reverse, like make it amorphous, or are you talking about like control the nanoparticle, the crystallinity?
Controlling, yes, the fraction of crystallinity or amorphization.
Oh yeah, so for the nanoparticle system, yes, we can control the amorphization, but not to all the systems.
Okay, and which parameter you change to control this?
So for that specific system, we use the method developed by Professor Yadong Ying. So we actually control the temperature when we do the colloidal synthesis. Yeah.
Okay, thank you.
So thanks again, Claire.
Thank you.
So the next talk will be given by Konstantinos Termenzidis from the University of Lyon, France. It will deal with thermal transfer management. To you, Konstantinos. The microphone is off.
Is it work now? Is it
Yeah,
better?
yes.
Okay, thank you. Thank you, first of all, to Gary and Renaud for the invitation. I'm very happy to be with you today. And my talk, my question and my talk is related also with the last talk. So I will show things that for phonons mainly, and how the amorphization can change the thermal properties of nanomaterials. So before this, let's make a small introduction. I'm working at CETIL, is a thermal laboratory at Lyon, at INSA of Lyon, is an engineering school, INSA, this is the campus, and this is a picture of one of the two rivers of Lyon. So I hope we can meet once in my city here. And another thing that I would like to make publicity is the ZDR. ZDR is a network, scientific network, French scientific network. The ZDR name means nanomaterials for energy application. So there are 60 laboratories, members of this group, with more than 550 researchers, and that they are doing elaboration of nanomaterials, measurements, simulation, and then also the application of the nanomaterials. So this network is supported by the CNRS and Thales Group, and the purpose is to create knowledge, and interaction between the different laboratories at French level about nanomaterials and energy recovery, conversion, management, and storage. So I will not show all what we are doing as ZDR, but I will show my own results. I'm working on thermal properties of nanomaterials, so thermal transport through the nanomaterials. And these are co-authors that they collaborate with me the last years, and the results I will show. They also work of all of these people. So I will start with a small introduction about what is happening when we go from bulk to nanoscale and the phonons. Yeah. So first of all, the structure changes. So you have a great number of surfaces, and the ratio of surface to volume gets important. You have also free surfaces, interfaces, the appearance of quantum effects, the amorphization plays an important role, and the heat transfer in these materials changes. It becomes different from the bulk. Why? Because you are passing from the diffusive regime to ballistic regime. What is important is the mean free path of the phonons compared to the dimension, let's say, of a nanowire or a superlattice. So if if the mean free path is of the same order of magnitude than the characteristic length, then we are passing to the so-called ballistic regime. You have also a more exotic effect like the hydrodynamic heat transport. And at this scale, what is important is all of the interfaces and free surfaces that appears, yeah, in the nanomaterials that have the same impact for thermal transport as the material itself. So I show here an example. If you have two thin films with an interface, the resistance of the two materials is of the same order of magnitude like the thermal conductivity of the constituent two films, two, two films. So we have to say also that the experiment is difficult. Here I show a scanning thermal microscopy tip, and yeah, it is one of the best experimental setup today to see nanometric variation of the thermal conductivity and temperature profiles, but still the experiment is difficult, and so simulation is a kind of solution. The challenges for the thermal properties, first of all, as you know, with your smartphone or your all electronic devices, yeah, the density of electronic devices getting higher, so you have the creation of hotspots, so you have to find the solution, yeah, to avoid mechanical failure. This is also related with the improvement of performances of devices and the lifetime of devices. There are also some application, a lot of application. The thermal management, for example, is important. The energy carrier engineering. So you have different energy carriers like phonon, electron, photons, magnon, plasmon, and coupling of all of these energy carriers. So there is also a lot of physics, and there is also application. Yeah, the application might be electronics, as we said, optical, optoelectronics, but also energy, renewable energy, biomedicine, and also the elaboration of nanomaterials. So let's don't spend more time. Let's go to more concrete examples. And so I divided the examples in two groups. One is to show what we were doing in nanothermal science from the years of 2000 till yeah, even now, yeah, with some concrete examples. But after 2015, we started to observe some more exotic phenomena, and this will be the second part of my talk. So let's go to the first one. Here we have modeled a nanowire with a modulated diameter. This is gallium nitride, no, this silicon carbide nanowire, I'm sorry. And we had a large and small diameter of nanowires. So what we show here is that the constant diameter nanowire has this thermal conductivity. This is hexagonal and cubic, but let's concentrate only on the cubic, let's say, silicon carbide. These are the values of thermal conductivity for the small cross-section, constant cross-section nanowire. And this is the modulated nanowire in diameter. You see that it has lower thermal conductivity than the small diameter nanowire. How we explain this decrease is because of the phonon blocking. You have parts here that they are larger, so some phonons, they are backscatter at the interface and they are blocking in this area. You can see also that the phonons, they are not transmitted the same way from the small to the large and to large to the small. So here is the phonon density of state, and you see that for the central part, that is the black and the red, for small and large diameter, you have phonon density of state that is the same, but the blue and the green that corresponds to the atoms close at the interface of the small and large diameter, you have phonons that they don't correspond to each other. So you have a kind of phonon filtering between the small and the large diameter. So this is one of the first examples that we I wanted to show. Another one is the network of nanowires in 2 dimension and in 3 dimension. Here, what we wanted to show that you might have sub-amorphous thermal conductivity. The thermal conductivity of crystalline silicon is 150. For amorphous silicon is only 1. So with this structure, you have 100% crystalline material, very light, but you have thermal conductivity that is under 1, that is the amorphous limit for the 2D and the 3D material. So we were suggesting this structure for thermoelectric devices. Yeah. There are some groups that they started to design and to elaborate this material. I know they made a 3D network of bismuth telluride nanowires. Yeah, that is the greatest for the moment thermoelectric material for the room temperature. The third example is a comparison between the theory and the simulation of phononic crystal. Here we wanted to see if the position of the holes in phononic crystals will play a role. for the thermal conductivity and also for the focusing of phonons. So here you have aligned holes of phononic crystal, and the second example is staggered holes. Here are the experimental picture, and we have shown that at 300K, the phonon they are not get focusing because the angle that the phonons they disperse in the material is the same for the blue and the red, yeah, for the aligned and staggered structure. But for low temperature, the aligned structure shows focusing of phonons. So these kind of materials might be used for the creation, let's say, of hotspot or the focusing of phonons. Of course, with different materials, but that was the concept, yeah, of this idea. And then always in the phononic crystal, there is always a kind of amorphization around the holes. You see here, there is a 1 or 2 nanometer amorphous material around the hole, and the other study about phononic crystal, it was exactly this, to see how the amorphization of the holes play a role. So here we have made a molecular dynamics simulation for the calculating the thermal conductivity of a thin film without any amorphization. Here is the thin film with the holes, this is the phononic crystal. And you see that the thermal conductivity from 30, it goes down to 3. So there is a reduction of 1 order of magnitude without amorphization. If we add amorphization of the holes, then we go further, we reduce further 1 order of magnitude the thermal conductivity. What I wanted to show also with this structure is that the amorphization parallel to the main direction of the heat flux doesn't play so much role as the amorphization of the same direction of structure. So when you amorphize surfaces at the same direction as the heat flux, then the thermal conductivity hinder much more than when the amorphization occurs in the surface parallel to the heat flux. The last example of this first part was about core cell nanowires. This is the classic core cell nanowire where you have the crystalline part in the center. This is a cross section, and this is a lateral cross section, and you have the amorphous part, and this is a more exotic nanowire. This is also possible to realize when you have a forest of crystalline nanowires and you bombardize with ions. If you bombardize them well, you might amorphize the center of the nanowire. Yeah, so this is an exotic but still really realizable structure. So again, with molecular dynamics, we have calculated the thermal conductivity of these two type of nanowire for different amorphous fraction, and we have seen that the classic nanowire has always almost double thermal conductivity than the exotic one. So it's not only the amorphous fraction that plays role, but also the position of the crystalline part compared to the surface or to the free surface of the nanostructure. To go deeper, we have calculated the phonon density of states for different groups of atom. So here is a crystalline part, here is the amorphous part. So you have an interface between crystalline and amorphous part. And here is the density of states for groups of atoms that they are close to this crystalline amorphous interface. you see that you obtain the crystalline density of states in a distance of 1 nanometer away the interface. So if you have interfaces of crystalline and amorphous material very dense, then the phonons, they cannot see the crystalline part of the material. They feel the amorphous part, and they might behave like an amorphous material, keeping a 50% of crystallinity. So this is also an interesting property for the thermoelectrics. Yeah, you can have thermoelectrics with higher ZT when you can combine crystalline and amorphous material. So that was the first part. I think I have time to develop the second part, that is new phenomena observed at the nanoscale. And I will start with the hydrodynamic regime. The idea here is to see how the heat flux is the profile of the heat flux inside a nanowire. So you have a nanowire. We have made named the non-equilibrium molecular dynamics simulation, and we have calculated the heat flux at a different distance from the center of the nanowire. So these are the heat flux, and here is the center of the nanowire. Here is the external surface of the nanowire, and you see that at the center the heat flux is much higher, and as you go at the edge, the heat flux is getting smaller. We had some discrepancy between Monte Carlo simulation. This is the Boltzmann transport equation resolved with Monte Carlo method. So here is the values at the surface, while for with molecular dynamics we found a difference. Yeah, this is the classical let's say physics. Here it takes effects that in classical physics we don't have. So yeah, molecular dynamics is also classical, but it somehow it feels other effects that you cannot incorporate in the Boltzmann transport equation. So what we saw here is that you have a Poiseuille flow, and to understand better, we collaborate with Xavier Alvarez from the UAB, the Autonomous University of Barcelona, and he explained the behavior with viscosity and memory effects. So Fuchs, Sondheimer is the same pictures here, yeah. Just we are using also amorphous cell to see also the effect of amorphous cell. If we go to this picture, that is similar to the previous one, you can see that the Fuchs-Sondheimer equation that people were using till now to show the effect of free surface show different behavior than our simulation and than the hydrodynamic equation fit that Xavier Alvarez made for us. And you see that the thermal conductivity, the heat flux is going almost to zero for the surface. Then we have also made some phonon propagation to see what is happening for different configuration. Here, what is important, what I want to show is the difference of different frequencies. So this is for 2 terahertz and this for 12 terahertz. You can see that phonons at 2 terahertz, they don't evolve well, let's say, they don't propagate well inside the structure. But for 12 terahertz, you have a nice bullet, yeah, that this is the energy that propagates inside the nanowire. So with this structure, you can see, first of all, the hydrodynamic effect and how you have this Poiseuille flow, and also how the phonon are propagating the energy propagation through the nanowire with the phonon propagative method. And another example that shows again the thermohydrodynamic and the propagative modes is a system that this was silicon, crystalline silicon inside an amorphous silicon matrix, and we have studied different shapes of the crystalline nanoparticle inside the amorphous matrix. So you see that for sphere or for truncated structure or for a nanowire mesh, you have different evolution of the energy traveling through this structure. To so this first phenomenon, it was about the propagating modes and the Poisson flow. The other example that I will show here is for the thermal rectification. So thermal rectification is the analogous of the electron rectification, and here we wanted to create devices that allow the heat in one direction, but they hinder it in the other direction. There are two different strategies in the literature. One is a geometrical strategy. This is what I use here. And the other one is an interface, but not parallel, but perpendicular to the heat flow. So to have two materials with different temperature dependence, with the thermal conductivity temperature dependence. So you use this effect for the thermal rectification. Here I use the geometrical effect for the thermal rectification. And so here the red is the crystalline material, the blue is the amorphous material. These are called tapered nanowires, and they are also realizable structures. And we have observed that systematically there is thermal rectification. The rate, it depends how you will calculate. I trust more these values, that is around 5% of rectification. But if you change the way that you calculate, you might have 80% of rectification. In any case, we have seen a systematic rectification with this structure, and you have higher heat flux from the small to the large section compared to the large to the small section of the nanowire. And we wanted also to see which phonos play major role to this thermal rectification, and the answer is the low frequency phonos that they create this thermal rectification. For higher phonos, you can see here the 12 terahertz. You see that the left and the right excited energy propagation is the same, yeah, left and right. But here for the small frequency, that you see that your energy propagates very well in this direction, but in the other direction, in the smaller direction, you have a lot of interference effect that hinder the thermal transport. So this is how we explain the thermal rectification observed in these structures. The more recent effect that we have observed is the phonon diffraction and interference patterns. Here we wanted to reproduce the Young experiment for photons, but we made it with phonons. So we have excited the phonons. Here is a crystalline material. Here is either a hole, yeah, or amorphous silicon. This kind of structure is also realizable. Nakamura group at Osaka University, he is able to make nano bridges, nano crystalline bridges, which can allow phonons in a very small area and hinder them in the big area. Yeah. So the work of Nakamura inspired this work, and we have shown, you can see here, the evidence of interference, diffraction and interference patterns of molecular dynamics is the black line, with the Kirchhoff model that is the red line. This is for distance 10 nanometer from the opening. Here is, you have at 50 nanometers, so somewhere here, and 100 nanometers away, so that is here, the screen here, yeah. And you can see that we have almost a perfect accordance between the experiment and the theory, the numerical experiment and the theory. So I don't know if I have 2 minutes more, or you want to go to questions.
But it is 10:40, so maybe you can yeah, 1 minute maybe if you
Okay.
want.
The last example is about the phonon. Thank you. Is about the phonon. Let's say tunneling. Here we had a silicon oxide structure with gallium nitride, crystalline gallium nitride nano inclusion inside. So I won't explain this, but I want to show you this. We gallium nitride is hexagonal structure, yeah, and two neighbor gallium nitride might be iso oriented or random oriented. Yeah, here it was iso oriented. I don't show the silicon oxide to facilitate the vision, and here is the random oriented nano inclusions. The thermal conductivity in this configuration, it was 25 watt meter Kelvin. In this one, it was the half. So somehow phonons, they pass from one nano inclusion to another, and they know the orientation of the neighbor nano inclusion. So if the nano inclusion is oriented, the heat dissipation is important. When they are random oriented, then you hinder your thermal conductivity. So I will not go further. I hope I convince you that phonons are very sensitive to surfaces, to amorphization and nanostructuration, and you can make phonon engineering to tailor heat transfer as you wish, yeah? To shield, to focus phonons, and or to create propagons using amorphous crystalline nanocomposite. I finished the presentation with saying that silicon is not a rare material and is not a toxic. So I think in our research we have to take also into account the toxicity and the abundance of the material, yeah, to continue going well. Thank you.
Thanks a lot, Konstantinos. I fully agree with the last message. So maybe we have one. I noticed one question from Gary. Yeah.
I was applauding, but I can't ask a question, but I think there is, Irma has a question.
Irma, yeah, Irma has a question. Please, Irma.
Hi, I'm Irma. I'm from St. Louis University, Department of Physics. So I have a question about nanobridges that you described in one of the last slides, the crystalline crystalline nanobridges. So you did show size effect. I missed the size of those bridges that were modeled or maybe experimentally done. So
This one.
well, either of them. So
Okay.
Bridges have width and thickness. So are we talking about thickness or the width of the bridges?
So here I think it goes from 2 to 5 nanometer.
Okay.
And we've made different bridges, and the length also plays a role. Here it was, I think it was 5 This one is 2 and 5 nanometers.
I see.
2 nanometer diameter and 5 nanometer of width.
Okay. Okay. So
But Nakamura, I think he is even made 1 nanometer bridges, yeah, crystalline bridges.
and could you remind us what kind of material those were made from?
This is silicon. Nakamura, he made it also silicon and germanium, and also silicon oxide inside the silicon, crystalline silicon.
I see. I see. Okay, thank you. Oh, actually, I have a one quick follow-up question. On the next slide, the thermal, so 25 watts per millikelvin. Well, I have a question. So this modeling shows, inclusions to play a big role, but these numbers are not by far close to some reported 300 milliwatt per millikelvin materials. So
But
is there something that could reach those few hundreds in by playing with density of inclusions or something else, or it's just kind of constrained by the material itself?
I think there are 2 or more effects. Yeah, one is the matrix. The matrix is amorphous silica.
Yeah.
So you see here that between the gallium nitride, it is an amorphous material. An amorphous silica has, I don't know, 1 watt meter
Yeah,
Kelvin.
exactly. Yeah.
So with a volume fraction, with a small volume fraction, you might have very important thermal conductivity due to the crystallite gallium nitride, yeah? And the EMA method, the effective medium approximation, gives these lines, yeah? So we are very far from the macroscopic thermal conductivity view. You have to double and triple the volume fraction to obtain these green lights that we have put here. These are the molecular dynamics. The square are the molecular dynamics results, and that's why we wanted to see, okay, to say what is happening if I change the orientation of the crystallites. So changing the orientation, we have find a lot of a big difference, yeah, between the thermal conductivity of the 2 configuration. And so one parameter I said is the matrix that has very, very low thermal conductivity. And another parameter is the diameter and the volume fraction, the total volume fraction of the gallium nitride. So the diameter of the crystallites plays a role, yeah? And also how much you fill your material with these crystallites.
Okay. Okay, well, thank you. Yeah, it's multiple factors, obviously. Yes. Thank you so much.
Okay, I think we have maybe unless Gary, your question is very short. I think we have to yeah, Gary.
No, I think we can go ahead and break, I think.
Yeah. So now we have a break, a short break. I propose that we meet again in 15 minutes, maybe at 11:05.
Yes.
Okay.
Thank you.
So see you again, and thanks again for the great talks.
Thank you.
See you. Hello. So I propose that it's time to get started again. So I am pleased to introduce Professor Alexandre Nomine from the University of Lorraine. He's going to talk about nanotechnologies and twin transitions. Please, Alexandre.
Okay, thank you, Renaud. I'm just sharing my screen. It should work now. And I just switch it on in full screen. So does it work well? Okay.
Yeah, it's okay. Yeah.
Thank you very much for the invitation to participate to this workshop. So today I will focus a little bit on the critical materials challenge, and basically I would like to start from the big picture, let's say, and we also already have seen it from the first talk that behind the green and digital transition, I mean, which should be seen together as those twin transition, there are a lot of metals involved. There are, of course, the abundant material like copper, cobalt. There are some materials that are more critical, like the rare earths, but not only, also the platinum. So this is why people say that we are switching from an oil era to a metal era. And I think at this stage, it's quite important to remind that we are switching from a non-renewable resource, which are the fossil energy, to an even less renewable resource, which are metals. If you think a little bit how to recreate new metals, it's a bit tricky, right? So this is why it's really important that we keep that in mind as materials fabricator, at technology designers, that yes, the end use is green, but we should also mitigate what is beyond and see the full cycle. If we speak about sustainability of the materials, of course, it's a complex topic in itself. It has a lot of definition, and I would not even be consider myself as an expert in this. But if we try to summarize the problem, I think we should first say there is a question of the abundance. We will grow our demand in materials. Can it reach some geologic limit or some limit of the production capability? The second point is environmental. I mean, yes, the point when you switch on a motor with gasoline, you pollute where you use. When we are speaking about other technologies like solar cells or like batteries, the pollution is at another place because it's at another level of the value chain. But it must be taken into account as well. So mining is not something neutral. And also something much less known, which is the byproduct, and I will speak a little bit later. Most of the materials we use for the nanotechnologies are not extracted from themselves, but as a byproduct of something else. So this will be my first, let's say, part of my talk. So yes, just a few numbers. This is geologic reality. There is 6 to 12 order of magnitude between the most abundant materials in the Earth's crust, like silicon or aluminum, with the rarest one, which are in the platinoid family, like iridium or rhenium. So this is absolutely huge difference of availability of the materials. So the rare earths, as you know, are not the rarest, unless they were say they are anyway few order of magnitude more abundant than platinum or iridium. Second point, there is also a very big difference in the CO2 footprint. For example, extracting 1 kilogram of iron will cost 2 kilograms of CO2. Extracting 1 kilogram of gold will generate 50 tons of CO2. This is a big difference. And the difference is because it's rare, it's expensive. And because it's expensive, for just one bottle of the equivalent, the volume of one bottle of water of gold, which is anyway 20 kilograms of gold, so this is anyway quite a lot of money, you have to extract one Olympic swimming pool of rock. This is where the CO2 comes from. And we do this because it's expensive, just because of this. Otherwise, it would not be interesting to do this, right? So just a few, let's say, few order of magnitude in the impact of the mining. And the third point I would like to draw your attention on is the byproduct. Here is just a paper from Nassar and al. From in Science Advance. It's a few years old already. And they highlighted that 61% of metals and metalloids elements have a companionality greater than 15%, meaning that more than 50% of the production of those metals is not made to produce this metal, but as a side product, we call it byproduct of another metal. And in this table of Mendeleev, you will recognize a lot of elements that we use in nanotechnology. We see gallium, that is a byproduct of aluminum. You see indium, that is a byproduct of zinc. And that generates basically some pretty unusual and counterintuitive mechanism in terms of economy. I mean, just here, let's take the example of rhenium. Rhenium, there is 45 tons produced per year. So it would just, the production would fit under my desk now. It's about two cubic meter or so. It's extracted out of the 290,000 tons of molybdenum that are produced as a byproduct of 20 million tons of copper. So basically, if you want twice more rhenium than what we have on Earth, you have to produce not 20 million tons of copper, but 40 million tons of copper. I prefer telling you that it's not going to happen. So basically what happens is that there will be, the price will just increases spectacularly, or more likely you will have shortage. So it means that there is no relationship necessarily between the offer and the demand. What may happen is that the person, the company who mines copper, if the price is too low, will not just extract the rhenium and throw it away. That's what may happen. But they will not double their production, even if you ask you are very convincing in asking. So this is, I mean, if I summarize this part, the byproduct, what is funny with them is that they are strongly non-linear. So if you have in the demand here, and here you have the price or the CO2 footprint, or even the capital expenditure needed for producing it, you have this kind of shape. So first you extract it as a byproduct. So the miner who is mining the major metal like copper or aluminum, basically selling the byproduct is just adding a little bit money to be a bit more profitable. So for them, it can be good to increase their economical performance. And the price does not necessarily vary much with the demand. They just sell it at a price and it does not vary much. But if you reach a certain point, the Demons threshold, then this is not any more linear problem, because then the demand cannot, the offer cannot sustain the demand. And for that, you need new mine. So what can happen? Most likely a shortage. So some company will not be served. They will not have their materials to work. That generates huge losses. The other thing that can happen is that then we need to start primary production of this metal. So we need to open a mine of, let's say, tellurium or gallium or indium. But first of all, it takes 15 years to open a mine. And secondly, then the CO2 footprint of this mining becomes very important, because those metals have a low concentration on Earth. So this is very important to have this in mind when we speak about the byproduct. And when I was speaking about the shortage, I mean, a few years ago, it sounded crazy to think that we have shortage. Any CEO of a company would say that, okay, we don't care. We have hedge funds to protect from any shortage. We don't care. And basically COVID-19 came, and we understood that a slight mismatch between the restart of the economy in the automotive versus the transportation and the semiconductor industry generates, according to Reuters, 11 million lost vehicles sell in a year. That's hundreds of $billions of turnover. So that's huge for just simple economic reason. The shortage I'm speaking about would be for geologic reason, and that's something it's much more difficult to cope with. So, and in general, shortage costs much more to a company than variation of price. And to be even more pessimistic, sorry to sound like this at this stage, is that the investment in the mining is at its lowest for 10 years, while everybody says that we will have to multiply the production of lithium by 21, of dysprosium by 4, and of cobalt by 4. Basically, all the metals production increase. So one part of the solution is recycling. Yes, with recycling, we have the primary mining and we have the urban mining, and there is a lot of methods that are available for this. So this is what we developed within a European network called EIT Raw Materials. EIT is for European Institute of Innovation and Technology, which brings together the different stakeholders from researchers to the companies to speak about it. And yes, recycling has a lot of advantages. It has advantages for the availability, for geopolitical reason as well. And if you check even environmentally, I mean, this is the variation of CO2 footprint. You decrease, for example, you need 2 kilograms of, producing 1 kilogram of iron generates 2 kilograms of CO2. Aluminium is 12 kilograms, and it could be reduced by a factor 3 to 6 for abundant materials. And if we speak about the precious metals, which needs a lot of, let's say, rock extraction, then it can be divided by a factor 10 to 50. It's still 1 ton of CO2 to recycle 1 kilogram of gold, but it's much better than 50 tons. So this is pretty impressive. However, at this stage, there is two warnings. First of all, ironically, if you recycle the, let's say, main mining product, which are here in the center of this wheel, I will just use the clicker. Yes, these are the primary metals that are extracted. And here is all the byproducts that are extracted from them. So for example, you can see here that gallium is exclusively extracted as a byproduct of aluminum. But if one day we recycle all the aluminum, we will not have gallium. So that might be a problem of recycling. But don't worry, we are not there yet. We are not recycling 100% of our aluminum, but at midterm, we need to keep an eye on this, especially for aluminum, zinc, where you have cadmium and indium, and germanium, which are important, iron as well, and probably copper, which are the most likely to be highly recycled. So tellurium and selenium might be in some kind of jeopardy. And well, we can see as we in different way, but ironically, all those metals are among the least recycled metals. This is for Europe. Sorry, I don't have the data for the US, but I presume they are pretty much close. For example, gallium and indium are not recycled. And this is, this is completely irrational somehow, because we need them more than ever, right? So at this stage, let's say before I go to the second part of my talk, which is more about material science, I hope you now are convinced that green and digital transition is highly dependent on metals. And that's what we saw in the previous talks. Metal economy is extremely complex. The byproducts, which are 61% of the elements we are using, are an undermined risk. And recycling, even though it is of the utmost importance, we have to recycle, it will not be a magic stick. Necessary, but not sufficient. So what do we do in my team? We do two things. First, we try to assess the risk associated with the green transition. And we also use it to discover new materials, and play with their properties. So this is how the project HEROES started. Sorry, HEROES is for Highlights on Europe's Raw Materials Sustainability. So it's because it's a European project. European Union funded. So what do we do is that we take into account the different impacts of mining. We integrate it into the green application or digital application, and we develop some multi-criteria evaluation. It works with 3-4 steps. First, we define an objective to scale up the production. Then we gather the different technical options. We do an impact assessment and a multi-criteria decision-making. I think it's easier that I show you an example. This was the speech of the EU commissioner in charge of the industry. He just said, okay, we need 11 million of electric cars. Okay, we know approximately what is the power that is the energy stored in a car. We can more or less deduce the energy storage capacity needed. We know the performance of the different batteries, and I saw some talk about it just before, and we have the order of magnitude. We can adjust if we have a new battery. We can therefore calculate the mass of materials that is needed, right? This is pretty simple so far. And from this, we show some figure of merit for the batteries. Here is another sustainability figure of merit. So we can understand how much CO2 will be emitted to extract the materials needed for the batteries. First of all, to ensure that the solution we are creating is not worse than the one before, and also to, let's say, rank them with the sustainability as a criteria, right? So here we could see the different families of batteries, and we could see, for example, the CO2 footprint associated with the material, right? So the one with cobalt are definitely better in terms of power capacity, but the one with iron are not that bad. I mean, in terms of, they are significantly better in terms of the CO2 footprint. And here we can have element by element so that we can understand where the footprint comes from, right? We can also work with the supply concentration. So understand, do we have a risk for our supply chain? So is there any concentration of the production? So yes, here again, we see some very, some difference from let's say, battery to battery. And we can do it for 11 criteria of sustainability, going from the footprint to the environmental risks, social risks, governance risks, supply concentration, the solicitation of the reserve. So here, for example, it's not in percentages, in fractions. So some batteries requires twice more than the reserves we've got on Earth. Okay, so reserves is a function of price. So, but anyway, it's a bit of a problem. Some of them requires to multiply the production of some materials by 78. So it's not going to be happening at very short term. So this is important to understand. But basically, okay, this is then what do we do with this data? We anyway have to choose. We anyway have to do the Green Deal, and we cannot stay as we are. Business as usual is not an option. So we have to find a solution, and we have to decide. So what we made is we created a risk network. So basically, these are the criteria that we calculated. And basically, you can give a different weight to different criteria. And you can ask also the expert to measure the interdependence of the criteria. So for this arrow inside, we ask experts to evaluate the interdependence. And for this colored box, we ask the consumers to tell us what is the best, what is for them more important for the consumers. So it's a mix of science approach and consumer approach. But what I just want to show you, I mean, is that using this one, we can create scenario. The scenario of the, I say the person who doesn't care about anything, or the wasted child, which are the same for us. So the wasted child wants everything, and some people are completely indifferent. For them, for us, they are the same people, because they attribute the same weight to all the criteria. If you want everything or nothing, it's the same weight in other terms. So this is the scenario number one. There are scenario of performance, just the price matter. And there is a scenario of resilience. I'm ready to pay more because I want to have a more sustainable use of resource, and I want to mitigate the risk. So I will give more importance to the risk mitigation and to the resource use. And what you can see, what is interesting, is that the bad player are more or less always the same. The good player are always more or less the same, but their ranking may change from one another. And here is, I think, where is our rule as scientists. We're not here necessarily to tell people this is the right option. We say, okay, if this is what you preferred, then that will be the best solution. Because at some stage, attributing a weight to these different parameters is not already in the field of a physicist or a material scientist. It's more about the citizen choice. So this is also something I think quite important about dialogue between science and the society. If you're interested about other field, here we tested this approach for seeing if metal organic framework has a potential for the data storage before even doing it till the end. So we kind of have, let's say, before investing in doing a device, so we tested, we have some let's say, papers about the storage capacity, the data storage capacity of the metal organic framework, which we could compare with the existing solution. And you can see that actually, yes, it could be a good player. Of course, there is a lot of scientific challenge to reach for metal organic framework, the performance and the resilience, the robustness of the process of the product that ST, MRAM, or flash RAM have. But here, what we can see is that yes, there is an incentive to do research in that field. So this paper is available in Advanced Functional Materials if you're interested, and I can reply your question if you like. So what is next? And also because it's about collaboration today, we are working already on solar cells, on hydrogen, impact on steel, on electronics. If some of you are interested to collaborate with us to do such studies on solar cells or LEDs or plasmonics, just drop us an email, or if you want to suggest any application, we are happy to investigate and collaborate on that field. You may also be interested to know that there will be trainings on the raw materials criticality assessment within our European project, and at University of Lorraine, we are in charge of training the researchers, teachers, editors of journals, and also grant evaluators, because we understand that this is part of the ecosystem, right, to assess performance of our nanotechnology. So you can follow us on our LinkedIn page, and when the training will be scheduled, it will be announced, and you are welcome to register. Right. So what do we do with this assessment? Then we believe it should be used for discovering also new materials. So yes, when I was learning materials engineering, we had these materials by design, also called as HB methods, and we had the properties of materials, and then we had to add constraints. And I was just trying to add the constraints that we need to have. Of course, we need to have the same performance as the devices before, but then we need to have a greener product with less CO2. Products must be affordable. They need to outperform or the previous one. Materials must be abundant to be produced in democratic countries with which we have, let's say, trade agreements, and et cetera, et cetera. And actually, you have a big chance to end up with, a null ensemble solution, right? So this is why, I mean, my belief is that we need to, to expand the library of nanomaterials. And for this, I mean, and I'm not being exhaustive here. I mean, what we do in my team is that we use non-equilibrium processes because we have some example. I will just make a very brief overview of them about how to discover new materials or just to play with the properties of the materials. So by non-equilibrium processes, I mean mostly plasmas. We work a lot with discharges in liquids. Electric discharge in liquids. We work also with lasers, laser ablation or laser irradiation in liquids. Some studies, but this is not my case, work with ultrasounds, or we work also with my colleagues in Slovenia about plasma jets. All right, so the first thing that is nice with non-equilibrium processes is that you can reach metastable phases of the matter. So what is interesting, for example, if you take copper and silver must not mix according to the thermodynamics, right? If you check the phase diagram, they are immiscible. But interestingly, if you manage to have a cooling rate of 1 million degrees per second, they will mix. And actually, 1 million degrees per second is not that hard to reach with a laser. And actually, this was a collaboration with Konstantinos, who is here. We even saw that for very small particles, we can reach about 1,000 billion of Kelvin per second of a cooling rate. So basically, it is absolutely possible to generate materials that are forbidden by thermodynamics using those processes. And what is interesting is here, for example, this is what you have here. Here is copper-silver nanoparticles. They was perfectly mixed within a single phase. But of course, when you anneal them, the thermodynamics is winning. And then you separate the phases. And what is interesting is here, just have a look at the scattering of the nanoparticles, which was measured by optical dark field. When the copper and silver are mixed within a single lattice, they have one resonance, which is around 580 nanometer. And of course, when you separate them, then you can tune the scattering with two peaks, which are two resonances, sorry, which are around 480 for the first one and around 700 for the second. Right. So basically, this is just an example of how we use metastability to play with the scattering of a single nanoparticle. Right. So we didn't add any other materials critical or not. Right. Here is a few selection of papers. These are not mine, but that I like really much, which shows the influence of microstructure. As a teacher of material science, I'm often explaining to my students how much the mechanical properties of materials is dependent on the defects, the grain boundaries, the dislocations, etc. And interestingly, when looking at the literature, there are some let's say studies showing that it's the same for optics, but it's not formalized. For example, one of my favorite one is it was made by Makarov and published in Nanoletters, show that how they managed to get a nonlinear response from pure silicon by increasing the grain boundary density. Because grain boundary can be seen as a local breaking of symmetry, and therefore you can have the second harmonic generation. And you got it for free in terms of materials, in terms of criticality. You use silicon, pure silicon. You just play with the process, and with they had some 10 to the 9, 10 to the 10 Kelvin per second cooling rate just to get the 2 nanometer grain size for free in terms of critical materials. This is why I like very much this study. Another one for a group in Japan. Here they managed to they use non-equilibrium processes with laser again to overcome the saturation limit of tin in silicon, and therefore the band gap of silicon become direct, and with a substantial increase in the solar cell efficiency. Once again, for free in terms of critical materials, because tin can be considered as abundant. Here is again with silicon and gold, how my colleagues generated some white light nanoscale emitter, just thanks to the segregation of gold at the grain boundary of silicon. Once again, microstructure, I think it's a parameter that we often forget about in terms of the optics. Also because the theoretical formalism is not here, and it's really terribly complex. But there, I mean, with the viewpoint of the critical materials, I think there are some incentives to investigate in that field. Finally, it would be a full talk, but I'm running out of time. High entropy alloys are also, or metal organic frameworks, are a family where we have a lot of choice. And I just plot the number of combination of alloys possible that are to be discovered. And we explored about 1,000 of alloys, a few thousands of alloys. And if we take 10 element high entropy alloys with one personal computational step, we reach the number of stars of the universe. So still a lot of work to do, which involve artificial intelligence, etc. But that's not the subject of this talk. That would be for another one. So the conclusion, I repeated the one before, so I will just go to the number 5. I think in general, when we speak about materials for a given application, green and digital, I think we should go beyond the simplistic cost-performance paradigm. I think we should take into account the sustainability. My example of byproduct is also how we can join sustainability and economy, because if you are at risk of a shortage, you are not only at risk of sustainability and biodiversity, you are also at economic risk. The second point is also that our group is looking for non-equilibrium synthesis process with lasers and plasmas, because we believe they open a new field of discovery of materials, or a way to tune the microstructure and therefore tune the properties, let's say, for free in terms of critical material. So we are trying to shift towards sustainable materials by design. So this is our, let's say, integrated approach. So thank you for your attention. If you're interested, don't hesitate to drop me an email. Thank you.
Thanks a lot, Alexandre, for this very nice, very inspiring talk. I guess we have some questions. Irma?
Hello. Hi. So very interesting talk. Very, very inspiring. So I have a question about so you are focusing on non-equilibrium processes and technologies, which is beautiful. You can do in situ measurements and see these wonderful degrees of freedom you can manipulate and exploit. Now, however, equilibrium processes or stable processes or steady processes would probably be as important, because I would like to ask you, do you have ways to see an implementation of non-equilibrium technologies or science so that it becomes a viable tool, not just for research, of course, but for something that you could practically use, because you don't want to do millions of degrees of gradient inside of your device if you want to use it, right? Same thing. We keep thinking always, how do we create technologies that we can carry on or become a consumable item that is you understand what I'm trying to say, right?
Absolutely. No, I perfectly understand. And I would have two level of answers. I mean,
okay, thank you.
If we speak about the metastable aspect of the materials itself, if we speak about thermodynamics, metastable and stable is the same. Just one is more stable than the other, meaning that with a certain amount of time, the metastable will end up at the stable. But for example, one application is diamond. Diamond is not the most stable state of carbon. The most stable is graphite. However, not speaking like James Bond, diamonds are not really eternal. It just takes 4.5 billion of years for them to come back to graphite. So, this is dependent from, let's say, state to state. Second example is maybe if you know a bit about steel industry, steel is often quenched, and they quench it to stabilize the metastable phase, which is austenite. But in that case, it's a few hundred of Kelvin per second, and it's pretty much stable. I mean, because it's kinetically trapped. So this is system dependent. I cannot give you a general answer. Some system will be very well in their metastable state, and they will not move unless they have unreasonable external stimuli. For example, in this case, we needed 600 degrees to turn to the stable state. So that's my first thing. It depends on the system, how well they are trapped, kinetically speaking. And I have no general answers. I know some system who works very well. Now, often people see these graphs, the one I'm showing, as a claim of saying we have dynamic system that can change its response on some stimuli. It's true, but it works only once. So it's for irreversible sensing. If we are speaking about in situ sensing, no, this does not work, because once you reach the stable state, you are trapped there and you have to go back to the liquid state. And this is very, as you say, very hard to implement. And the third level I would like to add about the synthesis, plasma processes, for example, there is a very, very huge know-how how to implement and upscale plasma processes. So sometimes we are surprised by what the industrials are ready to do and are able to do with the plasma processes. So the upscalability for the synthesis will be a challenge for sure. I mean, it's not something plug and play, but I would not be too pessimistic. Right? I don't know if I answered all your questions.
No, that's very, very, very relevant. Obviously, I definitely agree with you that for some materials and some systems, you could do different things, and for some, it will be more challenging. But that's definitely a very exciting topic. Thank you.
Thank you very much.
Thanks again, Alexandre. Unfortunately, we have to move on.
Thank you very much.
Thank you. So the next speaker is Jie Ruong. She's going to talk about nanostructures, structured materials for photocatalytic applications.
Let me share my screen first. Well, thank you for the introduction, and and Gary's invitation to participate in this workshop. It's my great pleasure to be here and share with you one of the projects that is actively going on in my group to examine the photophysical and photocatalytic properties of metal organic frameworks for solar to fuel conversion. So what we've been interested in this project is to develop a fundamental understanding of the catalytic mechanism of MOFs that can be used for solar to fuel conversion. And for this audience, I'd like to skip the introduction of basic idea of this slide and direct a point to the system that we are interested in, which is the electrode materials that combines a photosensitizer, which is light absorbing unit, and a catalyst. So we are particularly interested in understanding how light is absorbed by the photosensitizer, charge transfer to, which is followed by charge transfer to the catalyst and the catalytic mechanism. So there are many such systems that have been reported in the literature. Some of them are the homogeneous systems, which simply combine the molecular photosensitizer with the molecular catalyst. And some of them might be the heterogeneous systems or supported colloidal systems. For example, for the heterogeneous system, they may combine two semiconductors with different arrangement of the conduction band and the valence band. So people have done this with varying degrees of success and varying yield, but they also encountered varying degrees of difficulty. For example, the homogeneous systems often show good performance, high selectivity, and now they suffered from the difficulty associated with product. I need to move this guy. Product isolation and catalyst recovery, as well as the pore stability. So these problems are largely addressed by using a heterogeneous system, and now the selectivity and the mechanistic understanding becomes an issue. So then we ask ourselves questions, is there a better way to do that? So our strategy is quite simple. We hope to assemble the homogeneous components in a heterogeneous matrix such that we can marry the advantages of homogeneous and heterogeneous catalysts and simultaneously drop off their drawbacks. This leads to our interest in MOF materials. MOFs, the porous crystal materials composed of metal ions or clusters connected by organic linkers. This leads to the formation of a porous three-dimensional MOF structure. The benefits of MOFs for catalysis are multiple-fold. They have high surface area, large pore volume, which would facilitate maximizing the density of active sites, allows the easy access of substrates to the active sites. In addition, they have structural diversity because we can combine different combinations of metal nodes with linkers. This allows us to incorporate the homogeneous components for catalysis, as we mentioned earlier. For example, so we can design MOF structure to have its linker as the photosensitizer and the metal node as the catalyst, and vice versa. Or we can use both its linkers to assemble the photosensitizer and the catalysts. So there are many such systems that have been developed in the literature in the past decades. A majority of the system or the reports are usually focusing on documenting their design and stability and performance. There are very few work that are focusing on the fundamental understanding of the photophysics and its correlation with the MOF structure. So as a spectroscopist, so we become interested to develop like the correlation, the fundamental correlation between the MOF structure, particularly its metal node and the linkers to their photophysical and photocatalytic properties. But then the photophysical process often, for example, the light absorption, charge separation process often occur in ultra-fast time scale. So we need a tool that can resolve this process to study it. So the strategy we took is to use our expertise in time-resolved spectroscopy to investigate them. So in our group, we often use 3 time-resolved spectroscopy, which are all based on the pump probe technique. When the probe is in the optical region, we use it to study the excited state carrier dynamics. When the probe is X-ray region, we use it to investigate to study the oxidation state and the coordination geometry at the metal center in MOFs. And this time-resolved X-ray absorption spectroscopy is available in the 11 IDD Argonne National Lab, APS Argonne National Lab. We also use the OPTP, which is called the optical pump terahertz probe, and the time-resolved terahertz spectroscopy to measure the photoconductivity of MOFs. So this technique is this study is through our collaboration with Professor Charles Schmudmeyer at Yale University. We sadly lost him about 3 years ago, but the collaboration between his group and my group is still ongoing with his students and postdoc who was supervised by Gary Brudevig, but now one of the postdocs, he has his independent career, started his independent career at the University of North Texas. So this is, we'll continue the collaboration for future studies as well. In addition to this time-resolved spectroscopy, which allows us to measure the step, like one step at a time, we also use the in situ spectroscopy to look at the overall mechanism when the catalytic reaction is ongoing. We use the in situ X-ray absorption spectroscopy, which we often go to the 12 BMB at APS. So we collect this spectrum when the catalytic reaction is ongoing through this correlation of the spectral evolution with the catalysis time profile. We can tell. Often we can tell what is active side or what is responsible for the induction period we often observe in catalytic reactions and the deactivation process and sometimes the rate limiting step. We also do the in situ spectroscopy under the electrochemical conditions, which may tell us the active site and its structure. So with this idea in mind and the technique in hand, we started our journey in MOF field about a few years ago. So we started on a MOF, which is relatively easy to synthesize, and it's quite robust. It's the UL67 MOF based on zirconium oxide connected by the bipyridine ligand. We use the bipyridine ligand to incorporate a ruthenium polypyridyl complex as the photosensitizer and the cobalt complex as the catalyst. That's what we hope to do. I'd like to point out that by using the X-ray absorption spectroscopy, we found that the cobalt center is also coordinated to an additional solvent in addition to the chlorine and the nitrogen from the bipyridine. So this is important in the future fundamental studies because we found that solvent plays an important role. So that's I just want to point out here before we discuss the catalytic mechanism. So using this system, we can observe the efficient catalytic performance, which can last for more than 40 hours, and it's recyclable at least for 3 cycles. And the catalytic performance based on this MOF with incorporated ruthenium and cobalt complex is much higher than the physical mixture of a ruthenium complex with a cobalt only incorporated MOF, suggesting that the strategy we took is feasible. So if we incorporate both molecular species into MOF framework, can enhance the catalytic performance for the MOF system. So by now we still don't know what, although we hope to use the ruthenium as the photosensitizer and the cobalt complex as the catalyst, but we really don't know what exact role they play in catalysis. So it's necessary to confirm their roles using experimentally. So we use the optical transient spectroscopy to look at their excited state dynamics. We first looked at the ruthenium complex incorporated MOF. What we observed is only the excitation of ruthenium followed by its returning to its ground state. So that represents the intrinsic excited state dynamics for the ruthenium complex in MOF environment. We also looked at the dynamics for the MOF incorporating both ruthenium and cobalt. So now the case is very different. We saw the excited state decay of the ruthenium is much faster than its ground state recovery. This suggests that there is at least a portion of the excited state molecule of ruthenium didn't come back to its ground state, and it must become something else. To look at what's going on there or what it becomes to, so we used this X-ray transient absorption spectroscopy to directly look at the cobalt center and see what's going on there. So what we found is cobalt is reduced following the excitation of ruthenium, suggesting that there is electron transfer occurring from the excited ruthenium to cobalt. So this now makes sense why this system can perform the proton reduction reaction to generate hydrogen, because the cobalt is active for the proton reductions. So the electron transfer from the excited ruthenium to cobalt is around 1 nanosecond, and the electron transfer process from the TOA, which is the sacrificial donor we use for the catalysis, is 5 microseconds. So this means the oxidative pinching cycle dominates in this electron release cycle. After this, we expect that the catalyst enters its catalytic cycle. It can also undergo multiple species as proposed by Harry Green and his group, his people, based on a similar cobalt complex. So now then our idea next is to see whether we are able to identify one or few of the intermediate species in the catalytic cycle. So with this, so we again went to Argonne in the 11-12 BMD. So we set up the in situ X-ray spectroscopy when the photocatalytic reaction is ongoing to gain a decent amount of signal to noise ratio. So we have to increase the concentration of catalysis. So this leads to the occurring of an induction period in this one, which would not be good for catalysis reaction, but actually it helps us to understand what's going on there in terms of catalytic mechanism. So this is what we got from the in situ X-ray absorption spectroscopy studies, and the results are quite interesting. When we turn on the light, we observe the edge shift to lower energy, suggesting the reduction of cobalt. The original species of cobalt 2 likely goes to cobalt 1. When we turn off the light, the edge actually shifts back, suggesting this is a reversible process. And the cobalt 1 species must be active side for the catalytic reactions. And the time evolution for this energy, the time for the energy evolution consistent with the induction period time scheme, suggesting that during the induction period, the system has to accumulate enough concentration of cobalt 1 species before it can steadily generate hydrogen. In addition, we looked at the structure and the structure of the cobalt 1 species. We found that there are significant increase of the quantum number for the cobalt center. So this might be the additional incorporation coordination for the solvent species. As I mentioned earlier, so in the ground state, we see a coordination from the solvent, but now in the intermediate species, we actually observe the more coordination from the solvents, suggesting that solvent may play a role in catalysis. Based on these studies, both the time resolved and in situ studies, we got 2 important take-home messages. First of all, in the electron release cycle, actually, we also studied like other systems. No matter which system we studied, we always found that oxidative quenching cycle is the dominant cycle, which means the electron transfer from the sacrificial donor to the photosensitizer is the rate limiting step. And this is a model system, and these results leads us to tells us that we should not work on the model system. I think we are enough to do that. We should move on to a photoelectric system. So now in this case, instead of the electron transfer from the sacrificial donor to the photosynthesizer, we are looking at the total transfer from the photosynthesizer to the electron surface. So our idea next is, in order to facilitate this charge separation or to prevent the charge recombination from the user catalyst with the ground state of photosynthesizer or the whole in this case, we should improve their mobility in the materials. So this leads to our new direction on developing conductive MOFs as the photoelectron materials. And our in situ studies tells us the solvent plays a role in the catalysis. This is actually consistent with our catalytic experiments. We often see that a pH value, solvents, ligands, porosity of materials all matters, so suggesting the importance of microenvironment to the catalytic behavior of the materials. So in the next few minutes, I'd like to briefly introduce you to our recent progress in developing conductive MOFs as the photoelectrode materials. So our design strategy for a conductive MOF is to have a 2D MOFs with a metal node based on 3D transition metals, and their ligands are like either planar or contorted such that they can form the square planar structure. These are expected to enhance light absorption and photoconductivity. So the first the 2D MOFs we designed is based on a THQ ligand with metal node, copper and zinc. Our results for this MOF is quite interesting. We found that the external band, or you can either call the ground state bleach or external bleach, because we are not sure whether the MOFs are semiconductor or molecular species. Molecular, so we don't know which one to use. So here I just choose to use the external band because most of MOFs we have been working on have semiconductor property. So we found this external band is much broader in copper THQ than the zinc THQ, and also the wavelength shifts to lower energy for the copper THQ, suggesting that there is a narrow band gap for copper THQ. The broader peak external band also suggests it may have more dissociative states. So these two properties suggest that the copper THQ might have higher photoconductivity than zinc THQ. This is actually confirmed by our OPTP measurements. We saw a high, relatively high photoconductivity for the copper THQ. For zinc THQ, actually we didn't see it's not photoconductive. When we replace half of this copper by zinc, we saw about 50% reduction of photoconductivity. So the take-home message from this project is we believe that the photoconductivity we observed from copper THQ is due to the through bond principle, because if it's through space, which is often caused by the pi interaction of the ligands, if that's the case, we should also see the photoconductivity in zinc THQ. Since we didn't see it, we believe that the photoconductivity in copper THQ is dominated by through bond mechanism. So since we saw the distinct difference between copper and the zinc THQ, so we extended our study to other metal nodes, including the nickel and iron. What looks very interesting to us is by changing these metals, we can effectively change their band gap. In our case, iron has lowest, followed by copper, nickel, and zinc, which are confirmed by both the diffuse reflectance spectroscopy and our transient absorption spectroscopy, which show the trend of their the external band. The external band energy shifts to red from zinc to iron. So this actually can be explained by maybe, we don't exactly what's the cause of that. Two possible reasons could be I'm sorry, I forgot about to mention this photoconductivity results. Actually, this band gap tuning is also consistent, follow the same trend as the photoconductivity. And so what we propose here is the like, for example, the much higher photoconductive ion and a much smaller band gap ion MOF could be due to the presence of mixed valence electrons in ion. They have unpaired electrons, more unpaired electrons, this could contribute to the carrier density. So this is our results based on metal nodes, which mainly that the photoconductive magnetism mainly undergoes through the through band. But now we become more interested in knowing better about the correlation of the structure with the MOF structure with the photoconductivity. So we proposed that we hypothesized we may be able to enable the through space transport if we increase the size of the ligand. For example, so we synthesize these four ligands that can be used to construct the 2D MOFs. These ligands have increasing based on this from left to right. They have increasing number of pi electrons. So we hypothesized that with this increasing pi electrons, the pi-pi interaction between the ligands will be stronger, which may facilitate or eventually allows the through space charge transport. So we successfully synthesized 4 MOFs based on these 4 ligands. The results are very exciting. For example, let's look at the first 2 MOFs. This is the metal THQ MOF that we discussed earlier. This is the MOF based on HHTP ligand, which includes 3 benzene rings. So we found that even for the zinc HHTP, it is now photoconductive, which is in stark contrast to the copper THQ case. The zinc THQ case is not photoconductive. So this may suggest that by using HHTP as the ligand, now we enable the photoconductivity through the space. Another support comes from the copper THQ and the copper HHTP. Copper HHTP MOF shows much higher photoconductivity than the zinc THQ. This could either be due to the better contribution due to using HHTP ligand, also might be due to the pi-pi interaction, stronger pi-pi interaction between HHTP, which allows the through space charge transport. So these are the results. But we expect to have higher photoconductivity when we increase the size of the ligands, but our photoconductivity results actually is not what we expected. We actually saw the highest photoconductivity at HHTP, and with increasing size at the photoconductivity decreases. So now we think about what are the possible origins for that. So this, and these are very new results. I don't have the polished figure yet. So we saw very different XRD patterns suggesting they may have different stacking. We also see different absorption spectrum for this MOFs in the near region, where the copper HHTP, which shows highest photoconductivity, they show a strong broad absorption, followed by copper CTBC, this ligand, and then in the this copper HBC ligand that didn't have much high absorption. So we currently tentatively attribute this absorption band due to the free caryons or trap state, or maybe the semiquinone radicals. We are currently still working on that, and hopefully I'll be able to update you in the near future. So that's what I have for today. I hope I have convinced you that we are able to assemble the molecular species to the MOF heterogeneous matrix. And we can use that as light absorbing and the charge separation materials. And this system can do the proton reduction reaction to generate protons. Our transit absorption spectroscopy and the in situ absorption spectroscopy provided important fundamental insight to confirm the intermediate species and help us to understand the catalytic mechanism. Based on this insight, we now are developing two new directions. One of the directions is about photoconductive masks that can facilitate charge transport to prevent the charge recombination. And the preliminary results suggest that the metal node and the ligand size plays important role in the conductivity, and which we will explore further in future. So with this, I'd like to thank my group of members. Some of my groups are still at Marquette, where I was at, and mainly this work I talked mainly from the biochemistry who graduated this year. And I'd like to thank my collaborators, particularly for this project, Dr. Shalitam and James. Now he's a professor at the University of North Texas. And I'd also like to thank the DOE and NSF for supporting our research. Thank you all for your attention, and I'd be happy to answer any questions.
Thanks a lot for the great talk. If you don't mind, I propose that we ask Jir some questions after the next talk, because the next speaker must leave us in 25 minutes. So I propose that we ask some questions in 25 minutes for Jir and Prashant. Thanks.
Thank you, Renaud. You can hear me and you can see the slide, right?
Yeah.
Okay. Again, I will be giving this talk from Sweden. So I'm attending another conference here. So I apologize for rushing you guys. Okay, the talk is telling you sort of a broader view of where the semiconductor nanostructures are making a difference in photovoltaics. And this is our research group, current research group. And so these are the ones who make it possible. And I'm going to tell you their story. Just to give you an idea how semiconductor nanostructure evolved in the last century was first in 1990s, there was a big thrust for environmental remediation. And also there is a lot of work done on photocatalysis for generating solar fuels, especially water splitting, and which is now a hot topic in both water splitting and CO2 reduction. It also led to the evolution of dye-sensitized solar cells, and that's where the nanostructured films of TiO2 were coated with a sensitizer and generated electricity. And from then it moved on to quantum dot solar cells and those things. But one of the turning point that came, according to me, was this 1993 paper by Bhavandi group, where they made these semiconductor quantum dots. Before that, people used to make quantum dots, but the problem was you couldn't make very size selective things. And here you can see between 12 angstroms and 45 angstroms. This is the original paper. And you can tune the band gap using this chemical synthesis method. What used to be only a high vacuum technique on an MBE type apparatus, and now you can use a chemical bench or a chemical hood to synthesize these particles, and that led to a lot of revolution. And one of the advantage of these things we have been working is to modify the surfaces of semiconductors, because the accessibility of these dangling bonds makes it easy to modify with the dyes or redox couples or electron donors, electron acceptors. And more lately, it's also been used to 2D perovskites, where you can put these chromophores, very similar to what Jir was talking about with MOFs. Now you can do with these semiconductor materials and modify their properties. So just to give a broad outview, the capability of modifying the semiconductor nanostructures. And this was one of our early studies to demonstrate the size quantization effect in a solar cell. And we just modified the TiO2 with a mercaptopropionic acid, which bind to the TiO2, and then with the thiol groups bind to the CDSE. And that can inject electrons, and it is essentially a quantum dot sensitized solar cell that started. And we all can show that the smaller size particles had a greater IPCE, but blue shifted thing. And again, we have established how this electron transfer occurs depends on this band gap of materials. So again, that was just to give a background of it. And then we made the solar cells at that time, about 5% was a great thing, but things moved very fast. And if you don't like cadmium selenide, now there are other semiconductors like silver indium selenide, copper indium sulfide, and these are the materials are now gaining attraction, especially because you can now tune not only different band gap materials, you can also tune their size based on their things. So that's the size dependence on the band gap of the material. So these are the new materials one can consider. What makes these semiconductor nanostructure based thin film devices is they are solution processable, they are low temperature, the benchtop technology, and you can consider reel-to-reel production, and they have a, more importantly, carbon footprint. As you may know, the renewable energy, especially the energy production, the silicon photovoltaics has taken a major leap in providing the clean energy. But silicon itself has a large carbon footprint. To make silicon, you need high temperature, like 1900 degrees centigrade, and carbon as a reductant. So it takes about 2 to 3 years to offset the carbon footprint that is required to make the same panel. So that's why this is one of the things can fill in. Although cost is cheaper in silicon, but if you really want to reduce carbon footprint, one need to consider these new avenues. And for that one, recently, the halide perovskite has become a game changer because of the same process. And as I mentioned earlier, we started with dye-sensitized solar cell and solid-state DSSC and extremely thin layer absorption cell. And you can see here when the DSSC was like 10 microns. And when it comes to perovskite, now it is less than a micron thick. That means you are using less material for this, and that is a plus. And also it absorbs all the light in this very thin material. And the efficiencies have gone up. Now I think I just heard that it is with 25.7%, now it is 25.8% in comparison with organic PV and other solar cells that are occurring. So having said that, many of you know this lead halide perovskite. Again, it's a prototypical compound is methyl ammonium lead iodide, but this methyl ammonium can be replaced with either cesium or formamidium. So there are only 3 cations that can go into this cavity that is formed through this lead halide complex. And so that is much interesting. So other ions, cations are either too small or too large to accommodate. Although some of these recent studies have shown that there is some advantage of doping with rubidium in these cells. So that is the story of lead halide perovskites. And this is a typical structure when you make a perovskite solar cell. Is the large crystal you see is an FTO that is a conducting glass, and on which you put a thin layer of colloidal TiO2, about 50 nanometers, and then you put a methyl ammonium lead iodide, and then a whole conductor, which is a spirometad, and then on the top you put gold layer. And then you can characterize the JV curves and other materials. So this was about 17%, it got it long time back, but now we can easily make 22% in the lab, and it's a very common thing to make it. This is just to give an idea, a profile of a perovskite solar cell. Having said that, what is happening is there is another thing is coming up is this tandem solar cell. Because the reason is when something is commercially available in a cheap cost like silicon, it's very difficult to compete. And the question is, if you cannot compete, why not you join the race? So that's why people are putting these perovskite layers on top of this silicon solar cell. And one of them is Oxford PV. That's they're really getting into these things. And I think current the record is 32%. As compared to the individual efficiencies, it's about 28% for or 27% for silicon and 25.8% for perovskite. But by combining the two, you can get up to 32% efficiency. So this is really a good thing, and they are trying to commercialize. Again, this is a while back the Science read an article, but more interesting coming up. There is also another one that is coming up is these perovskite quantum dots. And this is also making a big splash in the sense that given other applications like LEDs and other things, you can get these cesium lead bromide, chloride, and iodide. And based on the halide composition, you can get a different band gap material. And this band gap material allows us to tune. And more interestingly, if you have a mixed halide, you can get in between these band gaps. So essentially, you can use a composition to tune the band gap. And typically in CAD selenide and everything, they used to use size, but here now you can use the halide composition to tune. And as a result, people have been trying to put it in solar cells. And this is early on, Joey Luther's group, they published a paper where they washed these ligands and got efficiency of 13.43. And Ranzhou Wang in Australia, they did the similar thing with the cesium lead, formamidinium lead iodide, and they claimed 16.6%. So this is where the stands with the thing with the nanostructured materials for solar cells. We have been working, and I'm not going to talk in detail, is studying this halide ion migration. One of the properties when you use this mixed halide in the dark, they want to stay in the mixed composition, but when you shine the light, they undergo phase separation to get these methylammonium lead bromide and methylammonium lead iodide phases. And that has been sort of a major way to probe the ion migration in these films. And for the lack of time, I will not talk about it, this one, just to tell you that some of the problems associated with it. And here's a cartoon that came out. The iodide is very shaky. Why it is important in solar cells? Because it leads to the hysteresis, because any migration during the operation and accumulation at the electrode surface leads to some capacitance buildup. And as a result, there gets more resistance. So when you do a reverse and then the forward, you get this hysteresis effect. Another aspect is also that if you use a mixed halide for solar cells, then your performance starts decreasing. So these are some of the effects there. And the reason is because you form these iodide and bromide regions, they sort of impede the flow of charge carriers. So this we have been studied earlier in this respect. What I'm going to tell you now is some of our recent work with the 2D and 3D interface. And the reason why 2D, 3D material, because this is one of the new areas in the semiconductor nanostructures coming up. So typically when you have this methylammonium lead iodide, you have this 3D structure, they stacked up. But if you replace the spacer cation with a phenethyl ammonium cation or a butyl ammonium cation, what you get is a layer structures. And the ratio of this methyl ammonium to phenethyl ammonium cation, which is referred as PEA here, varying this composition, you can get different layers. For example, if you completely replace with PEA, you get N equal to 1. And then you can again change these ones. And these are marked by this nice absorption spectrum that comes in. And these are excitonic transitions of these different materials. after about n equal to 6, you start seeing not any this quantization effect that it comes from this layered structure. And the band gap energy you can show here, and you can see here number of layers. So again, after about 6, you don't see any difference in this one. So what, again, you can do this excited state kinetics, and here is just a mixed layer structure. They clearly show these transitions coming from 1, 2, 3, 4. And you can use the recovery to find out their charge carrier lifetime. You can see here, most of n equal to 1 is a bound pair, and they all go very quick recombination. As you increase the layer, there are some escape the free charge carriers, and you can get longer lifetime. And when equal to 6, again, it behaves more like a bulk. And here is the charge carrier lifetime versus binding energy for the two different halides. So again, what you are getting here is a quantum well structure where the lower band gap is dictated by this perovskite layer, and this large band gap is from the organic layer. So one can tune these layers and the quantum wells based on the spacer cation and those things. So that is coming, again, this is very emerging. And you can also now, people are using a lot of photoactive material as a spacer cation. Okay, now coming back to the solar cells, there have been, again, I introduced earlier the perovskite solar cell. And one of the issues that is really currently people are attacking is how to stabilize this performance, because under the long-term operation, they do degrade or the performance decreases. So here is a recent science article by Moite and others. What they showed was if you put a 2D layer on a 3D, then the performance becomes very stable. And they very nicely demonstrated this thing, and they got a very high efficiency of 24.5%, and they preserves 99% of the initial value. And they call this inherits the intrinsic durability of 2D perovskite. At the same time, there is another from Juan Pablo's group in Georgia Tech. They claimed that upon annealing, if you heat it up, these bulky cations diffuse in the perovskite layer and cause changes in the structure and crystallinity of the interface. So the interface changes. It doesn't stay like a 2D, 3D material. And the performance of the bulky cation seems to stabilize after the initial drop. So there is, we start from here, there is a drop, and then it stabilizes as shown in this orange curve, whereas others started decreasing at higher temperature. So again, there is a very similar systems, but two different conclusions. And we looked into the literature, and there have been studies showing that the spacer cations can diffuse into this 3D, and there is no clear interface of 2D or 3D in this case. So we started looking into it, and this is one of our solar cells, what we made, and we heated up to 90 degrees. And so the cell temperature was about 85 degrees, and we recorded the cell performance at different times. And you can see here the voltage remains almost same in the first 23 hours, but the current started dropping down. If you take a IPC, again, it is a current response at different excitation wavelength, you clearly see a decreased performance, but more particularly where the 2D system is absorbing. And we also see very similar effect as that of Juan Pablo, where there is an initial drop, but it remains stable after that. Whereas the 3D layer, which is red color, continuously drops. Whereas the controls, they seems to do fine. The control is where you control at room temperature, not heated. So there is something going on with the 2D, 3D interface, and that's what we wanted to see. So here is under white light irradiation. This is where the 2D layer is, and you can get the diffuse because it's a very small quantity, and your 3D layer absorbs, you see as a very small absorbance. But in the emission spectra, you can see clearly that's a 2D emission and this is a 3D emission. When you shine the light, you can clearly see this one disappearing very quickly in about 180 minutes. This is after shining light. Whereas here also see very small changes, but not any significant. So when you record the absorption changes under white light irradiation in the different spectra, you can see the disappearance of the 2D material absorption that is corresponding to here, and that's one down here. And the carrier lifetime also changed during the time. This is what happens when you start heating, and same effect. Absorption of this 2D goes down. It's shown by the difference absorption, and the emission also goes down. And we can follow these emission changes with respect to different times, and you can also calculate the energy of activation for this. We also monitor the XRD, and clearly the heated sample showed changes in the XRD peaks compared to this 2D, 3D between blue and red color. So definitely that interface is changing with both light and heat. So now in order to see these different things, what we did was another simple, easy experiment where we put separately a 3D layer, which is of methylammonium lead iodide, and the 2D layer on another glass slide. And we slammed like a sandwich and then clamped it and put it on a hot plate. And we left it for a few hours and then opened it up, and you can see here clearly changes. This simple method allows what changes are occurring in the both layers to analyze for us. And here is what is happening in the 2D layer. This is before annealing and after annealing. This is in the 3D, and this is in the 2D. You can see here clearly that the peak disappeared and the new peak came up. As I told earlier, that when methylammonium composition gets in more into the 2D layer, it changes from n equal to 1 to 2 to 3. And clearly one can see in the emission now that the new peaks have started coming. So what happened is the methylammonium ion diffused into this 2D layer, and this spacer cation went into here. Because there is a small concentration change, we don't see much change in the 3D, but in the 2D layer, we see a lot of change in this one. So we can do the XRD in this one, and clearly this is after annealing that we see it, and in the 2D, again, the new peaks are coming as different layers are forming in this 2D layer when it heated up. So again, this sort of study tells you that what we got as an interface of 2D and 3D, it is not a fixed thing. The whole thing is very dynamic in nature, and these spacer cations can diffuse through and create a mixed or a gradient type structure at the interface. The idea behind adding this spacer cation was to provide more stability, because it is stable to the moisture and other things, but it may be making it more stable, but it is not because of this 2D, 3D interface, but it is because of the spacer cation. In fact, there is a Chris Brabeck group. What they did was they mixed these cations and checked the stability, and under certain conditions of these mixed halides, the mixed spacer cations, they saw it higher. So they questioned that the stability of this interface in PSC needs to be checked after prolonged cell operation. The intercalating organic cation introduces the stability. It is not the interface of 2D, 3D, but the spacer cations, when you incorporate them, they give us stability. And that's what they say is what is the one that's causing the stability aspects of it. So with that, I will end my talk. I didn't get as much chance to tell, but briefly I mentioned about how halide migration can affect the performance. And I focus more on 3D, 2D interface, and that showed that this is something people are trying to use it as to stabilize solar cell, but again, it is a dynamic in nature. The interesting part in this, despite all this attention in metal halide perovskite, everything moves. The cation moves, the anion moves, migrates, and even the lead can be exchanged with other metal cations. So this is the biggest challenge to stabilize this performance of the solar cell. With that, I would like to thank you for the opportunity.
Thanks, Prashant, for this great talk. So the session is open to questions for Gilles and Prashant.
Hi, Prashant. I'll go ahead and ask a question. Really enjoyed your presentation. Really interesting approaches you're taking. With the part where you clamp a 2D on top of the 3D, to what degree do you feel you have kind of control over what, like as you change temperature?
The temperature control is fine because we are controlling the hot plate and we're constantly monitoring the temperature from the top of the cell. And also the hot plate, it doesn't go above 90 degrees, and this cell is about 85 degrees. The clamping thing, the only problem here is it is not a really one-to-one paired film, but there will be some gaps, right? When you pair a film like that, but that is good enough. And you can see from the color change, these are actual films, that they do migrate from one side to the other. The reason for doing this one is when you make directly on the top of the film, you cannot analyze because you have to, like the previous one, which is, so when you deposit, typically what they do on the top, now you have a 2D, 3D together. So any changes that you monitor here is a composite effect. You cannot separate out. But this one lets us take it apart and analyze it separately.
Okay, no, very cool.
So, this could be for your photon source to see how this migration occurs. Will be a good topic for consideration.
Yeah, absolutely. I'm happy to chat about it more too. Very cool.
Yeah.
More questions for Gilles and Prashant?
I can ask a couple of questions. So maybe it's just a general question for Prashant, but you talked about a quantized the materials and the impact of exciton binding energy on reduced charge separation, essentially. So I was wondering is there in general a kind of a sweet spot for having these?
No, see, what happens is the binding energy for these lower layer numbers like n equal to 1, n equal to 2 is quite high. So these excitons, they don't free charge carriers. So one of the beauty of this, when the perovskite came in, was the long life, because binding energy was only about a few tenths of MeV. So as a result, whenever you shine the light, instant charge separation and the diffusion length was quite high. So that's was one of the reasons early on people realized that is what it makes this material give higher photovoltaic performance. But when it comes to these dimensions, reduce it, and you make these platelets of different layers, then the binding energy increases, and that's mainly because of these organic spacer cations. And so there is a correlation. This is what we try to do it in very early on, is charge carrier lifetime versus binding energy. And it seems to follow a some kind of a trend. So we didn't really do it. And the paper explains how do you calculate the binding energy and other things. And this is in agreement with the other reported values of binding energy.
Nice, thank you.
Yeah. But the nice thing is when you do the transient absorption, these peaks really separate out.
Okay. Maybe I can ask a question of Gilles, or does anyone have any other questions for Prashant?
Yeah, go ahead.
Gilles, on your through space control of through space charge separation with the ligands. So I wasn't sure if I saw what is the evidence for the increased efficiency for charge transport? Is that the main goal? Is increased efficiency?
Yeah, the main goal is, yeah, we hope to use both the through space and through bound charge transport. And that's our assumption. Like if we have both, and then the efficiency can be higher. But for the ligand part, we are not sure yet, like why it occurs, what's the origin. We are currently like looking at the possibility of the formation of the quinone, like using, we are looking at the EPR like that. FDR, so yeah.
I see. Okay.
Regarding the use of MOF for applications, what about the stability, the time stability of such a hybrid system? Is it robust or is it fragile?
It depends on the mass.
Yeah.
But we do notice, like for ruthenium complex, when we assemble that to mass, the stability increases compared to its homogeneous component.
Okay.
It does help, yeah. And we also have systems that like assemble a rhenium complex that's a CO2 reduction candidates to MOFs and COFs, and the system we studied. Then the stability increases too. I think that is attributed to the prevention of formation, like a dimer. Usually the formation dimer is often the destabilizing factor.
More questions? No, if not, it's time to warmly thank all the speakers who addressed very, very interesting and topical issues. So please get back at 1:30. Gary, it's very important that we start at 1:30.
Yeah, thank you, everyone. So it was a great morning. Really enjoyed all the talks. And we'll resume at 1:30 with the session on biomaterials for sustainability, and John Rogers will speak, will be the opening speaker. Thank you.
Thanks.
Thank you.
Nice lunch or dinner, depending on on your country.
Time zone.
Bye-bye.